we'll go from current slide. Okay. All right, let's talk about the announcements. There's several here. They published, I think you got it too, a final exam schedule. And when I saw this and thought about it a little bit and checked some things, I found out it was wrong. Not seriously wrong, but there were a couple of bad things on it. For instance, they have finals starting on Monday, April the 29th, whereas the academic calendar, the administrative calendar, everything else says finals start on Tuesday the 30th. So I haven't heard an answer back, and I checked the other day, and no one else has gotten an answer back. I don't know what the discrepancy is, but it's wrong here. Now, they had another thing wrong here, but they did correct on page 2, and this was written to us, not to y'all, but it said, all grades for mini-term 2 and regular term students must be submitted to the web suite system no later than 12 noon on Monday the 8th, which is sort of difficult because Monday's the 6th. But then on page 3, they have sort of the same thing written, except they say Wednesday the 8th. So I assume that's the correct information. But something's wrong with this, so I don't know what the resolution is. Here's the thing that I really wanted to emphasize, but I'm preaching to the choir here because y'all are in good shape. Okay? But next Tuesday, 1 week from today, is the last day to withdraw from classes for a full term or second mini-term courses. So that means some of the people who haven't been here, like those two I called, they should be removed. Hopefully they will be, but they've just never been here. Others, though, are way, way, way behind. So since we're on that subject, let me mention this again. Okay? With the understanding we only have a couple of weeks left in the term, right? Okay? And I've received uno, research paper from one student in this class. So please, folks, get your research papers done.
I'll change my
Topic? That's fine. Just get it in.
All right.
Okay. First labs, there's 1, 2, 3, 4 people haven't turned in the first lab. First test, 1, 2, 3, 4, 5 people haven't done the first test. And this is people that have been here, not the people that haven't been here. Lab 2, 1. Okay, sorry, not that one. 1. Only one person who's been here hasn't turned in lab 2. Let me go back and make sure I said that. I think I said it right. Okay. Lab 3, if I can read my writing here. 1, 2, 3, 4 people haven't turned in lab 3. Lab 4, 1, 2 people haven't turned in lab 4. Test 2, 1, 2, 3 people haven't done test 2. Lab 5, 1, 2 people haven't turned in lab 5. Lab 6, 1, 2, 3, 4 people haven't turned in lab 6. Test 3, 1, 2, 3 people haven't done test 3. And then we've had since then more labs. Lab 7, 1, 2, 3, 4, 5, 6 people haven't turned in lab 7. And lab 8, the last one we did, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people haven't turned in lab 8.
Was that last Thursday?
That's last Thursday. So I'll get you those probably during lab period, if that's okay. All right. Now, that being said about that, let me see if there are any other announcements. I can't remember if anyone from this class received awards at Honors and Award Ceremony, but if you did, congratulations. There were several folks that I did recognize that did get them, and I was real proud of you. So way to go on that. Okay. And your sister did, you said too, right? Yeah, good deal. I didn't know at the time. Huh? Yeah. I didn't know at the time until afterwards you told me your sister had gotten one. But does she look a lot like you? No, okay. Because someone went up there, I thought, boy, that looks, I was thinking it was you. Huh?
We don't look alike, but we're the same, like, personality-wise.
Oh, okay. Yeah. So, okay. So anyway, those are ones I can think of now. Okay. Let's talk about today then. Today, hopefully we're going to finish chapter 4 pretty soon, and then we'll get started in chapter 6. If we get far enough in chapter 6, then we can have our lab for the last 2 hours today in chapter 6.
Well, if we don't go to chapter 6, we're going to have the lab, or we still going to have the lab?
We're going to have class until 5:45, whether it's lab or class. We will be here. And basically, Wesley insisted that we take the entire time, so I can't argue with him. Okay. So, let's go with that. All right, where we left off last time was in chapter 4. It's evaporation and condensation. This is on page 105, top of the page. All right. I don't know if you've ever noticed or not, but we've been saying when a liquid reaches its boiling point, then it changes from a liquid to a gas, right? That's what we've been based on. But I don't know if you've ever noticed this. You can have a pan of water sitting out here in the room, and if you let it sit here long enough, ultimately it'll all evaporate away when it never has reached its boiling point. Okay? Does that seem a little odd then? Well, part of the deal with that is things evaporate according to how much energy each individual molecule has. Now, of course, when you're at the boiling point, all the molecules have enough energy to escape, or a vast majority do, and that's why you see it boiling. But individual molecules can change phase at any time. They don't have to be at a certain temperature, because all they need is enough energy to evaporate. Not that they have to be at that temperature. Temperature is the average kinetic energy of the substance. It's not what every molecule has. So evaporation, energy is required to overcome phase cohesion by individual molecules. Higher energy molecules near the surface can escape, and then they do. And that's what this figure will illustrate. All right? Now, this is showing the energies of a bunch of different molecules. And this is all sort of made up. Okay? And generally, the lower energy molecules, since they're moving more slowly, they're closer together, and they'll be denser. And the higher energy molecules will be a little further apart on average, because they're moving faster, and they're bumping into each other harder. So they're a little bit further apart. And then the highest energy will usually be near the top. Now, they haven't shown a good job of this, but the 5s down here should be collected around the bottom, but they're sort of mixed in. Then the 10s should be with those, and then there's a few 15s. But then the 25s, especially if they're near the top, if all of them were 25, this would be boiling, because they'd all have that much energy. But it's not. The average kinetic energy is down here around 11.5, and that's not enough for boiling. However, these are high enough. If they're near the surface, they escape. Okay? Because temperature is average kinetic energy, but individual molecules may have enough to escape at a lower temperature, because the average isn't high enough. Well, these two are going to escape then, 225s. Now, this is just representative. There's way more molecules than this in here. But what we have here are 1, 2, 3, 4 at 5, so those add to 20. 1, 2, 3 at 10, so that's another 30, so that'd be 50. 65 and 50 would be 115. So that's your total kinetic energy divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Divided by 10 would be 11.5 is the average kinetic energy. Okay? But those two escape. The 225s do. Well, that leaves you just lost 50. 50 out of 115, that gets you down to 65. divided by 8, that's the next slide here, 65 divided by 8, that gives you an average kinetic energy of 8.1. And sure enough, that does happen. When water evaporates, it cools because it's lost the kinetic energy of the higher energy molecules. Now, I've never seen or used one of these except in a picture. I've seen it in a picture. A canvas water bag. Okay? It's a sort of a porous bag that has canvas on the outside, and they use this a lot in, say, mountain climbing and stuff like this. This is your water supply. You use a canvas bag, and it very slowly, a little bit of water evaporates from it, very slowly, cools it off, so when you drink the water, it's not ambient temperature. It's actually below ambient temperature. If ambient was up here around 11 or 12, and you lost some, your remaining molecules have only an average of 8.1. So that would be cooler water, and it would be more refreshing to drink. Of course, you're losing it all the time, so you have to have something to supply the water as you're going. So the higher energy molecules near the surface can then escape. Now, condensation is coming back the other way. The gas molecules near the surface lose kinetic energy and then become liquid molecules again. Now, that's what happens if you pour a glass of iced tea or cold ice water. And you'll see those condensation molecules immediately get on the outside of the glass because the humid air in the room or outside or wherever you happen to be, those molecules get near the cool glass, they lose enough energy, and the water comes out of the vapor phase into those close by, change back to a liquid. And that's why your glass sweats, they call it. It's not sweating, that's condensing from the air. Okay? Now, that was evaporation and condensation. We've now moved to, and by the way, there is a picture in the book, and y'all probably won't recognize this because none of you probably have ever seen it, or you may have. Hanging clothes out on the line? Yes, my mom always did it. My grandmother always did it. I used to do it the first house we lived in Georgia when I lived with my brother there. Set up a clothesline. We had a dryer, but I preferred to let them dry. Didn't use the energy, and frankly, I thought, by and large, they smelled better, okay, because they had plenty of fresh air. But what you're doing is letting the air, the low humidity air, pull the moisture out, okay? And that's exactly what evaporation is. All right. 4.5 is thermodynamics. The study of heat and its relationship to mechanical and or other forms of energy. Okay? That's what it means. Thermo means heat. There it is. Dynamics meaning it's a constantly changing type situation. Okay? The relationship between the heat and other forms of energy, mechanical and other forms of energy. When you do thermodynamic analysis, that will include your whole system. You can't just look at a little piece, you look at the entire system. That may also include the surroundings. For instance, hanging the clothes out to dry, the system would be not just the clothesline and the clothes, but the ambient air around it. If it's getting ready to rain, they're not going to dry very fast because you have really high humidity. So everything around the system, everything else. It also includes the internal energy, that's the total internal potential and kinetic energy of the object in question. Now remember, there's a difference here. Internal potential energy would be that involved with phase change. Internal kinetic energy, that's involved with temperature change. So you are involved with both of those. Now, what are some ways thermodynamics happen? Ways the energy gets converted, either from heat to mechanical and other forms, or from mechanical and other forms to heat. Well, one is friction. Now, friction is one of these things that's not usually very positive. There are times when friction is very positive, and you really want to do it, but friction converts mechanical energy into heat. Good example of this, rubbing your hands together, pressing them together, rubbing, you can feel they heat up. Why? Because the mechanical energy of moving your hands with a little bit of pressure there, and that mechanical energy is converted to heat energy. Okay? That also happens in other places like your brake pads. Okay? Your brake drum, your brake pads, they're there, and when you press them together and the cylinder forces them together, that's when you change the motion of the car, you lose the mechanical energy of the car, and it changes to heat. Few of those don't feel out of them right after someone's been braking a lot. They are very, very hot. Okay? Now, going another way, heat engines are devices converting heat into mechanical energy. That's your internal combustion of the car, isn't it? You're blowing up gases in the pistons, and you're changing that expansion of heat into mechanical energy, turning the flywheels, which turn the shafts, which moves the car. Okay? Now, let's think about moving the car. If you didn't have some friction between the tires and the road, you're not going anywhere. You may be spinning your tires like crazy. If you've ever gotten stuck in a muddy field, you'll know that you can convert all the heat into mechanical energy, but if you don't have friction between the tires and the road, you're not going anywhere. So sometimes friction is necessary. In fact, then is totally necessary. Okay, other applications would be going in the other direction. For instance, a heat pump. It converts electrical energy into either heat, adding heat to a system, or removing heat from a system. Heat pump would be adding heat to the system. Refrigeration would be removing heat from the system. Okay? Organisms are doing this all the time. I didn't eat much lunch, but I ate some. And what my body is doing right now is converting that into energy. Exactly. That's why I can move around and stuff like this, because energy, food that I ate at breakfast this morning, the sugars and starches, are now being used to move muscles, move my mouth, make the noise, doing all this other kind of stuff. That's organism changing chemicals, stored chemical energy in the food into mechanical energy or sound energy or other types of energy. What does a hurricane do? A hurricane picks up energy from the water, heat energy from the water, and in the process it starts spinning like crazy and carrying that energy to northern climes. Now, I was I know Jerry Tracy because they go to our church, and I was in a book study sometime. The pastor was leading, but I was just in it, and Jerry was actually in the same group. It was a big group. And someone said, well, why do things like hurricanes have to happen? I just don't see any reason for it. And Jerry said, well, there is a reason for it. If it didn't happen, then the equatorial regions of the planet would be way too hot for anyone to live, and the northern and southern poles would be way too cold for anyone to live. The hurricanes are there to transfer energy from the equatorial regions and move it into the temperate regions. And that's what they do. Unfortunately, they make a big mess when they do it, but if we didn't have that, we wouldn't exist. Stars, that's happening all the time. At every star, there is thermonuclear reactions going on. Usually small molecules or atoms or molecules are being fused together to form bigger atoms or molecules, which are then giving off incredible amounts of energy. So you're changing mass to energy by Einstein's famous formula, E is equal to mc squared. A little bit of mass times the speed of light squared makes a huge amount of energy. Okay? Black holes are doing the reverse of that. They're sucking in all energy from everywhere else. Not even light can be emitted from them because the gravitational attraction there is so great, not even light leaves. So they are absorbing energy all around them. Virtually any system that you could imagine, if it has energy input or output, it's using thermodynamics. The heat and other energy relationships are constantly dynamically changing. So, there are considered to be 3 laws of thermodynamics, mostly formulated by William Thomson, which I think we may mention at the end of this chapter. We've met him before, not by his name, but by his title. Does anyone remember what his title was? William Thomson. Lord Kelvin. He's the one that basically came up with the concept of the Kelvin temperature scale. Okay, so
James.
Second.
James Prescott. I thought it was James Prescott who did the temperature too.
Okay, are you talking about Watts? James Watts?
Yeah.
Yeah, he did power.
Oh, okay.
Horsepower. He came up with a formula for horsepower. Okay.
Okay.
All right. Now, some people consider there to be a 0th law of thermodynamics, but this book doesn't mention it, so I won't go into it. But it's a very simple concept. Okay? But actually, these 3 laws are based on the concept. If you have an object A here at a given temperature, and object B here that has a given temperature, and object C in between the two. If object A is in thermal equilibrium with C, and C is in thermal equilibrium with B, then object A and object B are in thermal equilibrium with each other, whether they're touching or not. So a pretty simple concept, but that's what all the others are based on. And some people call that the 0th law of thermodynamics, but you don't have to worry about it because we're not covering it here. But the first law basically is another way of stating the conservation of energy. Components are, you have internal energy between molecules and atoms and things like this. You have heat, that's an external type thing, macroscopic thing, and work, which is a macroscopic thing. And these are the 3 components, and they have to balance. Okay? Now, it's stated in terms of changes in internal energy. Okay? And the sad news is, the book doesn't, the slide set doesn't show it. I don't think it does. Let me thumb through it quickly. I don't think it does. No. So let me go back and write it down for you. Okay? Now, first let me change my pen to something that will show up better, like bright yellow. Okay, internal energy is given the symbol U. Okay, internal energy is U. And we always, in terms of changes in internal energy, so we'll have U2 being the final, and U1 being the initial. Just like we do in other things. Okay? That's internal energy. Heat is Q. Okay, remember we've used that before in the last lab. Yeah, we did it in the last lab. Remember, Q is equal to MC delta T. Q is equal to L, your latent heat times the mass, those kind of things. That's the thing. Now, work is given in this, the symbol is just W. Capital W meaning work. Now earlier, no, I guess that's right. Capital W is work. Okay. Here's some items. All right. Now, because this internal energy is given in energy units, joules for instance, work is given in energy units, joules for instance, but heat is usually given in heat units, like calories or something like that. So usually they include here what they call the joule equivalent of heat, and that's they call J. So J times Q is, this is heat that you've converted into energy, or joules, okay? So that's what that stands for, okay? So here is the first law of thermodynamics written in these terms. If you start with the heat added to a system, joule equivalent of heat, but subtract off the work that's done by that system, then that gives you a change of internal energy, U2 minus U1. Okay? So your change of internal energy is going to equal the heat added minus the work done. Now, there are other situations that if work's being done on the system, that actually may be a negative, so you may actually be increasing the internal energy difference, not decreasing it. So there's lots of ways you can do, but that's basically the first law of thermodynamics. It's stated in terms of changes in internal energy, U2 minus U1, and applications of that is heat engines, your internal combustion engine. You add heat to the system by burning fuel that's doing work by moving the car, and the difference is the change of internal energy of the system. Okay? That's it. Now, here is one kind of example of it. Okay. Let's imagine that you had the air in this piston, in the cylinder. Here's your piston on top of the cylinder. You had the air and it was up at the top. Okay? But then I'm going to put a weight on that piston. So it's going to force the air molecules closer and closer together. I've just done something to it. Okay? I've changed the internal energy because now the air molecules are bumping into each other more frequently and heavily. That's probably increased the heat slightly, but some, because this did work on the system. Here is an external work doing work on the system, which is increasing the internal energy of the system. But then I turn around and add additional outside heat to the system. This is going to make the air molecules bounce faster and harder against each other and push the system up with the weight on top. Now we're adding additional heat to the system, JQ here, joule equivalent of heat times heat, this is in the energy unit, and it's doing work on the system, pushing the weight up. So now there is the weight, this was work being done on the system's doing work on the weight here. So it's reversing it. That also changes the internal energy of the system by the amount that you have there. Okay? Now, this is kind of getting in the way of my writing, so I'm going to remove the writing if that's okay. Anyone need that any longer? Okay. All right. Now, this is showing this next formula that's listed in your book. This is equation 4.8. Okay, and by the way, back here to this one I've already erased. That's conservation of energy. Change of energy is the heat added minus the work done by the system. Unless you did work on the system, then that is added to it. Okay? Now, here we have a different situation. Here, we're assuming that the internal energy doesn't change. Okay? And what we're doing, no, we're not assuming that. Okay. This is the heat energy model, the one we were just talking about. Okay, here's the heat engine that's adding heat to the system. Okay? This is going to increase the temperature of the system, and then you have work being done. That's the turning of the wheels, whatever. That's the work being done. So this is the output. The input is the heat being done. Oh yeah, this is it. Okay, I was misreading this. You have two different temperatures. We're assuming the internal energy is constant. Okay, and if that's constant, then the work out is strictly. If you go back to this formula that we had before, that this is joule equivalent of heat, so this is heat input minus work output, is equal to the change I can't remember what subscript they use. U2 minus U1. Okay, if you assume that this is zero, that the change of energy is zero, then what we have is the joule equivalent of heat, but you have a high heat region minus the low heat region, and that's equal to, if this is zero, then you can add W to the other side, and this is the basic premise of a heat engine. Your heat engine is here. We're assuming the internal energy is going to be fairly constant, so there's no change there. So what we have is a change of temperature. Your high temperature gases in your piston are going to force the piston down, do work on the system, and then wind up with a lower heat energy complement. Okay? Now, part of that blows out the exhaust pipe. Okay? Wasted, useless. Okay? We can't really capture anything from that. Some of it is used or is spent heating the water in your cooling system. Okay? And that's being blown off in your radiator. The fan there is dissipating that heat. Useless. We're not getting any good out of it. But when it gets down here, there's not much we can do with this anymore. But we use as much of this heat here to make work, which is turning the pistons, turning the flywheel, the shafts, and things like this, to doing the work that needs to be done. The change in the heat level there, times the joule equivalent of heat, is equal to the work output. Okay? It's just that JQL, there's not much we can do with that energy at the end. We get out as much as we can from the difference between the two. Okay? That's your heat energy model. And that's the second equation, assuming that the internal energy is about constant. Okay. Now, that's the first law of thermodynamics. Basically, conservation of energy. Change of internal energy is the heat added minus the work done. And if that change is the same, then the change of heat energy produces work. Okay. Second law of thermodynamics. This one's a little tougher to understand, perhaps. It's a little more involved, but here's what it is. There are three different ways you can express it. Okay? One of these is this one. No process can solely convert a quantity of heat to work. Like we just showed, some of that heat is lost. When it goes to the lower energy heat, you've extracted all the energy out, but it's lost. It's still hotter than it was to begin with, but you can't extract any more energy from it. That's the heat blown out of the tailpipe. That's the heat blown off the radiator. That's heat that you're not using to produce work. It's heat that's wasted. No process can solely convert a quantity of heat to work, as in heat engines. Okay. Now, some do a better job than others. Do any of you know what a regenerative braking system is? I think I've asked this question before. Any of you? I think Michaela knew. I think she said they drove a hybrid car. Any of you familiar with hybrid vehicles? No? Any of you in the room? Never mind. Okay. What a regenerative braking system does, rather than the friction of a brake pad on a brake drum producing heat, changing your mechanical energy to heat, what a regenerative braking system is basically a little generator. And it's taking the energy from the car and forcing it to turn a generator, which is we'll talk about this in the next chapter that we do, in chapter 6, that is making electrical energy from it. So what you're doing is taking the energy of motion and converting that to electrical energy that you're storing in your battery. which you can later use to make mechanical motion. So, but even that cannot convert all the energy heat to work. Some of it is still wasted. Here's another way of expressing the same thing. Heat never flows spontaneously from a cold object to a hot object. Okay? It just doesn't happen. But Michaela and Zaria do happen, and they show up. Just using you as an example. Didn't you say y'all had a hybrid vehicle? You didn't say that?
Yeah.
Oh, you did? Okay. All right. And we were just using regenerative braking, as an example. So heat never flows spontaneously from a cold object to a hot object, as in a refrigerator. Okay? Spontaneously. Okay? You can force it to happen, but it doesn't happen spontaneously. And here's sort of the dumb example I give of this, but it is really true. What if your air conditioner went out in the middle of summer and it was just baking in your house? Okay? Does this sound like a good idea? Open the refrigerator and freezer doors and let it cool the room. Sounds like a good idea, right? Would it work? No, why not?
First, your food gonna be spoiled.
Okay, let's assume that you got your food to the freezer out in the garage and you didn't spoil your food. Would that cool your house? Or at least the kitchen?
Probably kitchen, but not the whole house.
Okay. You say probably the kitchen, though?
Yeah.
Okay. So let me see if I understand this right. How does that refrigerator or freezer work? What's the first step in refrigerating your food? In the refrigerator or freezer viewpoint, not in the food point, but from the refrigerator.
It's a motor right there.
There's a motor, and what's the motor doing?
The motor, making it cold.
No, the motor is compressing a gas. Okay? This is what all air conditioning and refrigeration systems do. First thing you do, you compress a gas. That's a refrigerant. Or 230, whatever. I can't keep up with whatever the current one. Used to be Freon. They don't use Freon anymore, but it compresses the gas. As it compresses the gas heats up.
Yeah.
Okay? When you compress the gas, it heats up. That's the previous example I mentioned that. It heats up. Well, then what you do is blow the heat away. There's fans going on. Outside your air conditioning unit, go outside in the summertime and feel that air coming off those coils. It's hot. Hotter than the outside air, it's hot because you're blowing the heat away. Then you bring those compressed gases, if it's an air conditioning system, into your house, and then you let them expand quickly, which then pulls heat from the house as it's cooling. Okay? Heat goes from the hot object to the cooler object, always, never from cold to hot. Okay? But in your refrigerator, that fan is under the refrigerator, behind the refrigerator. So that compression that's going on is all right there. So as you open the door, that cold air comes out, the compressor that's in the refrigerator is right there, either behind or under the refrigerator, somewhere there, and or on top. The old ones had it on top.
Yeah, the old ones had it on top.
Okay, and that's happening. But guess what? That heat is being blown right into your kitchen. So you see, no, it actually heats up your room because no process can convert a quantity of heat to work, or this one, you are going to actually get warmer. Okay, so no, it won't. Here's the third way of expressing the same second law of thermodynamics. Natural processes tend toward a greater state of disorder. That state of disorder is called entropy. In other words, the entropy always goes up. Now here's a real dumb example of that. I want you to imagine, have any of you ever bought a deck of cards? Yes, you have, okay? When you first opened that deck of cards, how were they ordered? Were they?
No.
You weren't. Every deck I've ever opened, now it's not been many, but ever, always starts with the ace of spades, the king of spades, the queen of spades, the jack of spades, the ten of spades. It goes down through all the spades, and then you have all the hearts, and then you have all the diamonds, then you have all the clubs, and they're all in order. Because they do them that way to make sure they have all the cards in the deck right? That's how they were packaged. Okay, so let's imagine I open the package, throw away the box, I have all the cards, make sure they're all not stuck together, put them on a blanket, and 4 of us get together and start tossing them into the air. Okay? Now, do you think I'll ever get those to land back in the same order I started? No. You're not even going to get them all to face in the same direction. As soon as you start tossing, some of them flip over, some of them do this, they never come back even into a stack. But if they did come into a stack, they wouldn't be in the same order they started. Everything, natural processes, tend toward a greater state of disorder or entropy. The entropy goes up. Okay? Now, there's 2 reference scales here for the second law. One of these is the object's external energy. Okay? That's the energy of global coherent motion. That's the energy associated with work. For instance, moving your car forward, turning the wheels, turning the drive shaft. That's your external energy, okay, associated with work. The other reference is your object's internal energy. The energy of the microscopic, chaotic, incoherent motion that goes along, that's associated with heat. So, anytime you do a process, some of it is work. For instance, that picture we had before, producing work. Some of it is just heating up the system. Okay? This usually is non-usable. That's usable. There's always some of that. No process completely produces work. All of it produces some incoherent, chaotic heat. Okay? Low-level heat. Heat never flows from cold to hot, always from hot to cold. Natural processes always tend to increase the entropy, which is the disorder of the system. Okay? Now, here's the first statement. I probably have already said it. You can think of the conservation of energy in the heat engine. The output energy, the input energy is the energy you put into it. The energy of the stored chemical bonding in the fuel that you're going to burn. Okay? Your gasoline. Okay? Whatever it is. Your output energy is the work that you get out of it. Okay? Now, the conservation of energy says input energy equals output energy. Yeah, energy cannot be created nor destroyed. Okay? But the efficiency of a heat engine is the work done. That's part of the output energy, just part of it though. The work done per unit input energy. Remember, the output energy includes work, but it also includes that low-level, incoherent, chaotic motion that is heat. Okay? So the efficiency of a heat engine is the output work per unit input energy. Never can you use it all. Remember that first law. The second law says efficiently cannot equal 1. It's always going to be less than 1. The work done is always less than the input energy. Always. No system can convert heat all to work. Some energy is always degraded, and you can't ever use it again. So here is the way to express this. Your input energy is your Q hot. Okay? That's the original burning of your fuel. Okay? The heat. Your output is both the work plus the low-level heat that you can't ever retrieve. That's going out the exhaust pipe, blowing off the radiator. That's the parts you can't use. Okay? And here's Brandis. Right? Okay. Okay. This is never 0. QL is never, ever 0. There's always loss there. The low-level heat. So the efficiency is the work part that you got out divided by the Q that you put in. Now, the bad news bears is that I don't know about modern cars. They may not be as bad as they used to be. I'm sure they're not. But in general, your efficiency of a typical internal combustion engine is probably on the order of 20% or lower. That you have more Q loss here than you have work. 80% is going that way, 20% is useful. Okay? It's pretty sad. Now, things like hydraulic jacks and things like this, really, really efficient. Never one, but really, really efficient. You get a lot of the energy out that you put in. Okay. So here's the second statement. This is conservation of energy, the heat pump. The energy arriving in the high temperature region is energy from the low temperature region plus the work needed to move it. Okay? Now this is a heat pump. Basically what you've got here, you have your gas, just like we had for a refrigeration system. You start compressing it. That's adding energy. That's the work done, the compression. You started with gas at some temperature, whatever it was, and you compress it, you're adding more to it. That gives you the heat on the high energy scale, the high energy, Q sub I H. Okay? That's then what you blow your air across, and that distributes to the house. That's what a heat pump does. What you're doing, you're taking the ambient material, whether it's a fluid, whatever it happens to be, the refrigerant, you're adding work to it, which is compressing it, and then you're blowing that heat into the house. Okay? Any chill that's left over, you try to expel that to the outside. This is in the wintertime. Okay? The work is required to move the energy from the cold region to the hot region. When you get to the hot region, that's where your heat pump. You blow your air across that, and that's where you get your heat. Okay. Upgrading of energy by the heat pump is accompanied by greater degradation in energy elsewhere. So in other words, sort of a weird way to say it, you're upgrading this low temperature region, but when you're operating the heat pump, there's probably some friction and other things here, the oil's heating up, whatever. You can't always get all that out of it. You just can't. You can get more of it out than you can going the other way, but it's still not. That's the second law of thermodynamics, the second statement. Everything, you can't, energy doesn't move from a cold region to a hot region spontaneously. You have to force it to move, basically. Okay. Now the third statement. Real processes are typically irreversible processes. Many of our things that we do, we try to have them as reversible, but real processes are usually irreversible. So the measure of disorder is what we call our entropy. The second law of these terms, the total entropy of the universe is continually increasing. Okay? Can this go on forever? No, you think not. Okay? It just can't happen forever. So that means the universe, and some people will claim this, is going to die a heat death. That's what we're talking about here. Natural processes degrade coherent, useful energy into incoherent, chaotic, unusable energy. The available energy in the universe is diminishing, and eventually it leads to the heat death of the universe. Unless there's some rule out there we don't know about. And one of those is, what in the world are the black holes doing with all that energy? Is it being redirected somewhere else? I don't know. Now, the direction of natural processes is always toward more disorder. I gave the example of throwing a deck of cards into the air over and over again. They're never going to come back in the same order they had to begin with. Ever. ever. You can do it till the cows come home. You'll never get them back in that same order. The other way to do this, and this may be a little simpler, is if you spill a glass of milk, you can't do anything to unspill it and get it to go back into the glass. It just doesn't happen. You know, no matter what you try, you'll never get it all in there. In fact, it's just going to be a bigger and bigger mess. Okay? Everything goes to a state of disorder. I bet you back when you were teenagers, which maybe some of you still are, I don't know, I bet your mother experienced this when she tried to get you to clean your room. Did your room ever try to clean itself? Did it ever go back into greater order? No. It always tended to go to more and more and more disorder. Another maybe practical example of that. How did you get more order? You had to put work into the system. That's why they call it work, right? All right. That was the last slide in the slide set. There are a couple of interesting little things. One is the mistakes and misunderstandings. Can something make its own fuel? No, I don't think so, okay? Actually, they tried it over here in the automotive department of using sort of wasted energy to hydrolyze water and then mixing the hydrogen back in with the fuel to burn it and see if they could retract it. You never can get more out than you put in, ever. So it just wasn't efficient, okay? The guy whose blurb is mentioned here is Count Rumford, Benjamin Thompson. I think I mentioned him before, really. Remember? Remember what he was known for? He's the one that he was American by birth, but if you notice his dates there, 1753, which was 20-some years before the American Revolution, to 1814, which was another 35 years after the American Revolution, maybe more than that. I'm doing it quickly in my head. But let me first get Rhodesia here. There you are. Does anyone else come in since I called roll? Okay. And the sad news about Benjamin Thompson, he was an engineer, a good scientist. And what he's most known for scientifically, and why he's mentioned here in the book, is the fact that he was the one, the engineer, who was boring cannons somewhere in Germany, working for some German military, perhaps the Holy Roman Emperor, somebody like that, boring cannons. They pour cast iron cannon shapes and then bore the hole for them so that they could explode the ball, thing and the balls fire out. So he was having the drill out there. He had some poor old workhorse going round and round and round, turning the bit. But when the bits got dull, they weren't doing any good, so you changed bits, and they got dull pretty quickly. But he noticed when they did get dull, rather than boring the holes like they should, they just heated them up. So he had one cannon that was faulty. Maybe it had a crack, maybe it was off center. I don't know what the problem was. He decided to do this experiment, okay? He decided to get the dullest bit that he had, that they had basically tossed out but hadn't thrown away yet, dullest bit he had, and start the horse going in a circle and put in the coldest ice water he could get. He was in southern Germany near the German Alps, bringing in some of that really cold alpine water, filling the cannon with it, and start the horse walking. In less than an hour, he had the water boiling. Wait a minute, folks. Heat is not some intrinsic property of the material. Heat is related to the work done. That was the first time they saw the Joule equivalent of heat. Count Rumford was the one who showed it. Later, James Joule quantified it, and they named the unit after him. Now, what was the sad news and why Count Rumford is a count, he was born in the colonies in the U.S., okay? They weren't the United States yet. They were the colonies. And when he was in his early 20s, when the war was beginning to break out, he didn't want to fight in the American Revolution against the British. He favored the British. And many others did too. He wasn't the only one. And he made his way to England. He didn't fight against the Americans, but he didn't fight for them either. And because he was a really bright scientist, young guy, and a good engineer, and he defected and came to the British side, they gave him the title of Count. He wasn't born into aristocracy, they gave him one. And that's why he became Count Rumford. Okay? There is some thing I've noticed somewhere in the past before. Some people think he may have been a compatriot of Benedict Arnold, who was actually arrested, tried, convicted, and executed as a spy for the British. Glad Rumford got out of there before that happened, if indeed he was a compatriot of Benedict Arnold. Okay, but there's your person. This cannot be your source. You can get your ideas from here, but you have to get your source from some external part if you're writing on him or anybody. So let's do example 4.8. Okay? Let's see if we have... Okay, here we have some room. A heat engine operates with 65 kilocalories of heat. Now, what's the symbol we usually use for heat? Y'all remember? Went over it just a few minutes ago. That's your capital Q. That's heat. Okay? Now, that's what you're operating with. That's the heat supplied. So this is a Q on the high energy side. High heat side. Okay? And exhaust 40 kilocalories of heat. So the 40 kilocalories of heat, that's your Q sub L. The low level heat you can't use. Okay? Now it says, how much work did the engine do? Well, if you remember, work is, if you remember that, I think it was the second formula I gave you, you have to convert the heat kilocalories into joules. So that's the joule equivalent of heat times QH minus QL. That's the amount that did work. Okay? Well, the joule equivalent of heat, and it's given in several places in your book, but I'll use the one they got right here, is 4,184 joules is equal per, let me put it this way, per 1 kilocalorie of heat. Okay? So there's the joule equivalent of heat. Multiply that by the difference between QH and QL. And what's that difference? 65 to 40? Difference between 65 and 40. It's not that hard to do. Oh, pull out the calculator. 25. 25.0 kilocalories. Okay. Kilocalories cancel out, and that gives you, someone punch it in your calculator, 25 times 4,184. Anybody? 4,184 times 25.
102.
Say again?
102.
Not 102, I don't think.
102,000.
The book had 104,000.
104,600.
Yeah, 104,600. And that would be joules. Well, that's an awfully big number, so you get a
Yeah, that's the right
Here's Dominique.
word.
Okay. We're going to wind up with a decent class size, maybe. Okay. Now, because you only have three significant digits there, 3 there, you have 4 here, but that doesn't help. You only have 3, so let's count off 3. 1, 2, 3. Look to the right. There's a 6, so let's move this up to 105,000 joules. Or if you wanted a bigger unit with a smaller number, what would that be? Anybody? Smaller number, but bigger unit. What metric prefix means 1,000? Kilo. 105 kilojoules. Okay, 105 kilojoules. Now, they didn't ask this question, but I'll go on and ask it. What was the efficiency of this heat engine? Well, the work you got out of it was 105 kilojoules. The work that went into it was the 65 times 4,184. In fact, I'd be tempted hard to do. But that's what you would do. You would find this is your work output, multiply 65 times this, that would be your input, divide by that, and you'll see that your percentage is really, really low. Okay? But let's not take time to do it. We need to move on. All right, but that's how you get efficiency. Now, you'll hear me say this every chapter. Nothing replaces reading the chapter. So please read the chapter. Preferably read it before I talk about it, and then you might want to skim it and read it a little bit more after we talk about it. But do it beforehand. But if you haven't beforehand, read it now. Then you have the summary, which is a pretty long summary here. A lot of words in italics. Those are pretty important words, so I'd pay attention to those. Then there's a summary of equations. This chapter has 8 equations. I would pay really good attention to those. Your key terms, that's about normal amount. Most of these are the italicized words or some of the italicized words in your summary. But then the applying the concepts, 43 questions, maybe a few fewer than normal, all multiple choice. Answers are given. If you can get those, then those aren't going to be the same ones on your test, but they're going to be covering the same material, so pay attention to those. Questions for thought, 17. That may be 1 or 2 more than normal. For further analysis, 7. That's a few more than normal. And there's an invitation to inquiry that you can look at if you want to. The parallel exercises, there's a group A. If you have a big book, the answers in the back. I don't know if the small ones have answers in the back or not. Group B, nobody has the answers in the back. Okay. So that finishes chapter 4, which means Thursday, the last 30 minutes, we'll have our test on chapter 4. So be prepared for that. We are skipping chapter 5. If you have the small books, you don't even have chapter 5. And we're moving on to chapter 6. Okay, I wish we had time for 5, but we don't have time. We're running out of term. I think chapter 6, electricity, far more important to you probably than sound. Okay? So let me get out of the slide set. And here's Seth. So we're still missing Austin, who usually comes in after he finishes his other class. Chris, we haven't seen. Rashad, we haven't seen. And the Williams brothers, we haven't seen. They aren't brothers, I'm just kidding. DeAndre and Kelvin. Okay. I don't think they're brothers anyway. Okay. So let's get out of this, get out of that, and let's get into chapter 6. just as a reminder, today we are going till 3:45 because there's no test today. So we'll be going to 3:45. It's now 2:31. So we got about an hour and 15 minutes. So let's see how far we can get in chapter 6. Now, they entitled the chapter just electricity. But as you'll see in the core concept, we're really talking about more than electricity. The first part of the chapter will be electricity. The second part will be magnetism. Okay? And basically then we'll be combining both electricity and magnetism. So electric and magnetic fields interact with each other and can produce forces. There can be electric forces, there can be magnetic forces, and there can be electromagnetic forces. And we'll be hitting on all of those cylinders. Okay? So let's move to concepts of electricity. This is 6.1. All right. Here's where we begin. Way back in time, people realized there was something special about certain materials. And it started out really as sort of a parlor game. Someone would take a piece of amber. Anyone know what amber is? Okay, amber is usually considered a color, which is sort of a palish yellow kind of color. But the reason is that it basically was tree sap, as in pine rosin or something like that, that had been fossilized into a mineral. And that's what amber was. And it was a nice mineral that you could make jewelry and things like that out of it. But if you took a piece of amber, raw amber, and rubbed it with wool or fur, either one, and then sneak up behind someone and touch them with it, you'd shock them. Okay? And people didn't know why it happened, but it made a nice parlor game, and people would be shocked and scream or yell or something like that. That was the ancient mystery, amber effect. What in the world was going on there? Okay? It was centuries, maybe millennia, before somebody, and this guy happens to be J.J. Thompson. I think we'll see him come up again in chapter 8. That's the next chapter we'll do, the last chapter we'll do. But he identified there are these negatively charged particles, but they're really so tiny, it's hard to even think of them as a particle, but they are, apparently, that are called electrons. And what happened when you rubbed amber with wool or fur, what you were doing was knocking electrons off the fur and attracting them to the amber. So then when you snuck up behind someone and touched them with it, they get a shock because those electrons that were excess electrons that were on the amber now then went to the person and gave them a electric shock. Now we don't do that much anymore. But when I was working for Southern Research Institute in radon research, we were doing a lot of projects in several areas, but I was mostly working around Polk County, Florida, which is in central Florida between Orlando and Tampa, and just sort of right in the middle of the state. Lakeland and Bartow were the areas, the cities we were closest to working in. And we usually stayed in as cheap a hotels as we could find because we didn't want to spend any more of our research grant money into housing. We wanted to spend it in the research. And these usually had fairly cheap polyester carpet, I would guess. And when you scuffed your feet along these and then reached for the door, and the door frames for the hotels were usually metal, you could sometimes get shocked. I don't know if you've ever experienced that or not. It used to be in some of the cheap vinyl they had in car seats, if you scooted across the car seat with, say, cotton pants or something like that, across the vinyl car seat and reached for the door handle, sometimes you would get a shock, okay? And that's all this, that something is rubbing electrons off something else and someone's getting a shock, okay? Sometimes it goes the other way. If you take silk and rub it on glass, then the electrons from the glass move to the silk, so the glass winds up positively charged. And then you touch someone with it, the shock feels the same. Now the electrons are coming off the person onto the glass rather than going from the amber onto the person. It still feels the same. What you have is one object is charged one way, another the other. Okay? Now, that was the ancient mystery. Today we understand that. J.J. Thomson was one that helped us understand it. The basic unit of matter is the atom. Now this is especially elemental matter. Okay, for compounds, you would say it's the molecule, but molecules are made up of atoms. Basic unit of matter is the atom. We talked about it before. But the atoms are also made up of other units. Okay? But the atom is the smallest unit that you can have of a given material. The smallest unit of iron that you can have, or copper, or molybdenum, or anything else, would be the atom. Hydrogen, helium, carbon. The smallest unit would be an atom. The atom's made up of other things, but they're not carbon or other things like that. Atoms are made up of electrons, which are these tiny little, incredibly tiny little subparticles that fly around, but they can't have a negative charge. Okay? But there's also a nucleus. Now this nucleus is very, very small. Incredibly small, but it contains almost the entire mass of the atom. Incredibly small, but almost the entire mass of the atom. It's made up of positively charged protons and neutral neutrons. Now the protons and neutrons have almost the same mass, and they are fairly massive. But they're stuck together in this tiny little nucleus, surrounded by this enormous cloud of electrons flying around the nucleus. The electrons have almost no mass whatsoever. They do have some mass, but it's incredibly tiny. Less than 1 in 10,000 what a proton or a neutron would be. So a tiny amount of mass, okay? Flying around, but occupying a huge volume. Whereas all the mass is concentrated in a tiny little volume in the center of that electron cloud, okay? So the nucleus contains these protons and neutrons, which are either positively charged protons or neutral neutrons. And they would be in here in this tiny little nucleus. Now this is showing a helium atom. Okay, not that it really matters, but 2 protons, 2 neutrons, that's what makes up helium. And really, if this were helium, you wouldn't have this outer ring here. You just have that inner circle there with 2 electrons. Because for the 2 protons and 2 positive charges, 2 electrons would be 2 negative charges. Neutrons have no charges. Okay? So therefore, this outer ring shouldn't even be there. That inner ring would just have 2 electrons, not even a ring. Cloud would have 2 electrons somewhere in that cloud. The nucleus would be smaller than one of those little bitty dots there, and the cloud would be much bigger than what you see here. Okay? But all the mass is in that little bitty dot, and all the volume is being occupied by those 2 little electrons flying around in general. Okay? So that's your structure. Okay. So what is the electron charge, or electric charge? It's the charges of matter, and these are inseparable properties of certain particles. Like I said, the electrons have a negative electric charge. Now this is a little unfortunate because, and we can probably blame it on a great statesman, but also a very good scientist and engineer, Benjamin Franklin. Benjamin Franklin was largely responsible. He's one of the 5 people that wrote the Declarations of Independence. Thomas Jefferson is known to be the main writer, but he was involved. But Benjamin Franklin was also one of the main guys writing the U.S. Constitution. Jefferson wasn't very much involved with that because he was over being the ambassador to France, I think, at the time. So he wasn't involved in writing the Constitution. Benjamin Franklin was. But Benjamin Franklin was also a fantastic scientist, an incredible engineer, and a newspaper editor. I mean, he did all sorts of and he happened to name and say, well, let's say the electrons are negative and the protons are positive. Lots of things would have worked out a lot better if he'd have randomly changed them around and said the other way. But we'll call it, because he said it, the negative electric charge. Protons contain the positive electric charge. Protons, though, are trapped in that tiny little nucleus. Electrons are flying around this cloud way far from the nucleus. So what's the charge interaction? Well, you have electric force. Now we're going to talk about that a little bit more in a little bit, but let's just mention it now. Here's the basic definition. Like charges repel each other, unlike charges attract each other. We know that, right? Okay. Now, there's some real problems with this. Because guess what? Those protons, the positive charges, are packed so tightly in their tiny little nucleus. Why is it exploding? Because those positive charges are trying to repel each other. Well, because there's some stronger forces at work there than we are talking about now. So, extend that. The electrons, however, are in this cloud around here, and they do repel each other. They try to get as far as they can from each other, but the positive charge of the nucleus holds them in. Okay? So like charges repel, unlike charges attract. Okay? Now, what is an ion? What we've been talking about before is a neutral particle. Two protons have to have two electrons for it to be a neutral atom. Okay? It doesn't matter how many neutrons, well, it matters a little bit, but not to charge purposes, because they're neutral. Okay? But if you happen to have an imbalance there, then you have an ion. It's a non-zero net charge, either from gaining or losing electrons. Okay, so let's take that amber that we rubbed with the fur. Okay, we knocked the electrons off the fur onto the amber, so amber have excess electrons. The fur now has deficit of electrons, so it's negative, positively charged, but the amber is negative charged because it has excess electrons. So that would now be ions of amber, not atoms of amber. They're not really atoms, they're molecules. Or if you rub the glass with silk and you knock the electrons off the glass onto the silk, and therefore the glass now would be positively charged because it lost electrons to the silk. So the ions are when you have either excess electrons or a deficit of electrons. Let me point this out to you. You never gain or lose protons. Protons are trapped in that tiny little nucleus. The only way to get them out is to have a nuclear explosion. We don't want those happening, okay? They don't happen naturally, okay? So, well, not in our experience, okay? They do on the sun, but not in the other. So what we have is always the gain or loss of electrons. Either an object is gaining electrons, becoming negatively charged, a negative ion, or it's lost electrons, becoming positively charged. Never gaining or losing protons. Ever. Gain or loss of electrons. Okay. Now here is an example. This happens to be a lithium atom. I know that because lithium has a plus three protons in the nucleus. It has two electrons in the inner shell of electrons and one flying around there in the outer shell. That's how lithium lives. That's an atom, a neutral atom of lithium. Okay. Because this one electron's out here all by itself, it's real easy for it to get lost, to go to somewhere else, maybe to a chloride ion or something else, and it loses it. And if it did, then lithium still has 3 protons in the nucleus. Nothing changes that, but now only has 2 electrons in the orbit, so it becomes a net positive charge, a positive lithium ion. That is what happens, and that's what is shown here. When that one electron gets drawn off by something else, pulled away, now you have no longer a neutral atom, but a positive ion, lithium plus 1 ion, okay, because 1 electron has been removed. It got ripped off by chlorine or fluorine or something like that and left the picture here. Now, what often happens then, the chlorine now becomes negatively charged, the lithium positively charged. Now they're attracted together and they form a lithium chloride molecule. That's another story. So we'll get there in the chemistry part. Okay, so that's what your electric charge is. Gain or loss of electrons. Very seldom, never gain or loss of protons. Occasionally, you have movement of whole ions. Like in your battery in your car, you actually have ions moving around in there. And most batteries do. Okay. Now, this does not happen. They're just showing this for illustrative purposes. They're showing lithium picking up an extra electron. It doesn't do this, not in nature, okay? So don't expect it to. But if it did, that would then become a negative ion because now it has an excess negative charge. 3 protons in the nucleus, 4 electrons in the outer thing, a net -1 charge. Lithium doesn't do this. Chlorine doesn't. Lithium doesn't, okay? Chlorine never loses electrons, it always gains them. Lithium never gains them, it always loses. But the general purpose is met here. That would be, if it ever happened, a net negative charge, negative ion. All right, now we get to something maybe we're familiar with but didn't know why it happened. This is the good old parlor game of shocking someone with a piece of amber or something like that, or shocking yourself when you walk across cheap carpet and touch a metal door, or sliding across the Naugahyde seat in your car with cotton club pants and you get a little bit of a shock. This is all due to static electricity, which also is what happens when you put clothes in a dryer, and some of the clothes may be silky or some other kind of material, others may be cotton. You put them all in the dryer together, and then you try to take them out, and they stick together like crazy, and when you pull them apart, you hear it go. That's electricity, static electricity. Or when you pull them out and your pants are all stuck together, static electricity, okay? What is happening there, we have what we call an electrostatic charge. Now here's static, there's static. What does static mean? Anyone know? Static. If you put an O-N in it, that would almost spell station. Maybe put an A-R-Y on it, stationary, fixed, in place, static, not moving. That's what static charge is. Electrostatic charge means static charges are electrical in nature. In other words, gained or lost electrons. Okay, electrostatic charge. Stationary charge confined to an object. Okay? Now, what are some of these? Friction. Okay? Don't know if this has ever happened to you. It doesn't happen to me much because I don't have enough of it to happen. But if you've ever, now, here's the requirement. Your hair needs to be clean, and it also needs to be dry, preferably very dry. And the air needs to be pretty dry. And you take a comb, a rubber comb, say, and comb your hair, and then you notice your hair follows the comb. That's electrostatic. You've taken the rubber comb, combed your hair, taken electrons off your hair onto the comb, but when you pull the comb away, the comb's negatively charged, your hair is positive charged, it follows it. And you messed up your hair, okay? That happens. That is a charging mechanism. Friction rubs electrons off of one object onto another object, so you wind up being charged. Another is contact with a charged object, okay? For instance, walking across the cheap carpet, scuffing my feet with rubber-soled shoes. Oh, ears. I'll find you. I know, I just can't find. There you are, Chris. Okay. It's here. And you beat the buzzer. Okay. All right. Almost through. Okay. So, contact with a charge object. Okay? You scuff your feet along with rubber-toed shoes on the cheap polyester carpet, and you reach for the doorknob and you get a shock. Well, I hated for that to happen because it always surprised me, and it didn't hurt really badly, but it was just a surprise. So what I found I could do was pull out my room key. Now, this is back when they had room keys and not swipe cards like they do in a lot of hotels today. And if I had my key in my hand and I went and touched the doorknob with it, I would sometimes, if it was dark, I could see the spark happen, but I wouldn't feel shocked because it left from here. So you see, I was charged, but the key was in contact with me, so it became charged, and it's what exchanged the shock, not me. I prefer the key to happen. And literally, you could see it sometimes. And I've seen it sometime at night. I can't think what the material is. It's a synthetic material that the blanket is made from, and the sheet is cotton. And sometimes when you pull it back, if the light's off, you can see the little sparks happen. I don't know if you've ever noticed that, but it can happen. Also, I've noticed this too. I don't see the sparks, but I can feel them. We have a golden retriever dog. She loves to be rubbed, so she'll stand out on the stoop. I'll rub her, and I'll feel the little charges because I'm rubbing electrons off. You can feel that. So contact with the charged object. Now, another way that you can charge something is by polarization. That's a reorientation of induced charges without changing the charge. And this is a thing you may have seen someone do in the past. And here's Rashad. Good to see you. We're going to wind up with a fairly good representation today. We're only missing Austin, who usually comes in a little later, and then the two Williams, DeAndre and Calvin. So hopefully they'll be coming in too. Okay. You may have seen this done before. I know you've seen it happen, but you may not have realized what was happening. Okay? If you take that comb that you combed your hair with, and your hair was clean and dry, you see if your hair is a little oily, it doesn't exchange charges well. So if it's clean and dry, and we don't have that many times in the South when we're all that dry, so we don't notice it much down here, but comb your hair, and you have that comb, and you have little bits of paper on the desk here. Comb your hair briskly and stuff, and then hold the comb near the paper, and one piece of paper will pick up and go toward the comb. And then it'll pick up another piece and another piece. Well, guess what? Those pieces of paper are neutral. They're not charged. But when you hold the comb, which has negatively charged electrons you wiped off your hair, okay, and those electrons pull, because like charges repel each other, unlike charges attract, the little piece of paper the electrons will go to the other end of the paper, leaving this end positive, so it's attracted to the comb. But that end of the paper is negatively charged now because electrons went down there. That's polarization. Reorientation of the induced charges without changing the net charge. It will hit near the next piece of paper. Its electrons rush to the other end, leaving this end. So it'll pick up, and sometimes you can pick up a whole chain of little pieces of paper with that comb because of polarization induced charges. Now, this also happens, unfortunately, at our house. Does anyone know what cobwebs are? Okay. They're not webs at all. They look like a web, but what it is a little, it's not microscopic, but very little dust particle is made to have a little charge with it. It's called a colloid, which usually has a charge. And it attaches to another dust particle, to another, to another, to another. After a while, you have a hole. So if you reach out and touch it, they all fall apart because they're all individual little dust particles. Okay? Unfortunately, we live in an old house and it has its number of cobwebs in it. And anytime you're running a forced air system and stuff, you're knocking off charges, dust particles get charged and they stick together and form cobwebs. Okay. Some of that through polarization. All right, so here's the gal. She's washed her hair recently. It's a dry day, not here in the southeast, but a dry day. So she decides to comb her hair with a rubber comb, and that looks like a great thing to do. But as she does that, at first her hair is neutrally charged, same number of plus and minus. The comb is neutrally charged, same number of plus and minus charges on it. But when she combs her hair with the comb, she knocks electrons off the hair onto the comb. So now the comb is net positive charge, and the comb is net negative charge, and she pulls it away. Now the hair filaments are repelling each other because they're positively charged, and they try to repel each other. So now her hair looks worse than it did before she tried to comb it. And when she pulls the comb away, it follows it because the comb is negatively charged, the hair is positively charged, and those are attracting. And yet they're repelling each other. So she's really upset that she's having a bad hair day. Okay. Again, that doesn't happen that much here in the southeast because we have very moist air a lot of the time, and so we won't notice it as much as other areas will. Places that you dry, and that thing about the bed sheets and the spread, of course, the blanket, that happens more in the wintertime when you have heated up the air and dried it out some. So you tend to have more of those charges. Okay. This is the second one I was talking about. That same comb she had that had negative charges here, you hold it near a little scrap of paper. It's not going to be a big piece of paper like this. A little bitty scrap of paper. The positive charges are attracted to the comb. The negative charges are going away from the comb. While like charges repel, unlike charges attract. You have reoriented the induced charges in the paper without changing the charge. Okay, it's still neutral, but the positives are up here, negatives here, and they will then attract each other. See, originally this is way too evenly spaced, but neutral paper, unpolarized, once it's polarized, then you can pick up other pieces with that. All right, I have been turning pages. Let me turn pages now. There's a sketch. You can do that if you're interested. Concepts applied, static charge, and it says this application works best when the humidity is low. Very seldom do we have low humidity here, so it probably wouldn't work. But now we're getting into where we are now, electrical conductors and insulators. This is the bottom of page, the right-hand column of page 143, rapidly going to 144. What electrical conductors are materials that have free electrons that are easy to move around, okay, throughout the material. That's what makes a conductor a good conductor. Now, remember we talked about conduction in heat? Guess what? The free electrons conduct heat very well, too. That's why the aluminum seats conduct electricity very well. The rubberized or plastic stuff does not, because those are big old molecules that don't have free electrons. Okay? But, getting back to here, electrons are free to move throughout the material. Anytime you add a charge, it dissipates and gets as far apart as it can from the other because the charges move easily. Most of your metals are good conductors, relatively good conductors. There is a type of carbon, graphite carbon, which is a good conductor too. Okay? Now, we'll get to this a little bit later, right now. There are other things that make really good electrical insulators. Here, the electron motions are restricted because there's not free electrons to move. The electrons are held basically in covalent bonding rather than electrostatic bonding. So they're held together and not allowed to move. So they make good electrical insulators. Added charge tends to remain right there on the surface, and that's what static electricity is. Rubber is a good insulator. Okay, glass is a pretty good insulator. Amber would be a good insulator. The charges tend to remain right there on the object, not dissipated like they are in a conductor. An example would be glass. Wood is a pretty good insulator, as long as that wood is dry. If the wood has a lot of tree sap in it, or wet water is wet with water, it's going to be conductive. Okay, but dry wood would be a great insulator. Diamond, which is pure carbon, is a good insulator. Why is the difference? Graphite carbon is one electrical structure. Diamond is basically a two-dimensional array of the atoms are arranged in two-dimensional sheets, and diamond, three-dimensional structure. Same material, very different electric structure. These, the electrons are free to move. These are really, really fixed in place. And then we have another class of materials that we didn't used to know much about, and these are called semiconductors. These conduct or insulate depending on the circumstances, as in temperature, direction of current, those kinds of things. Computer chips depend on semiconductors. They allow a charge in one direction at one time, resist charge at other time. Solar cells, same thing. They accept heat from the sun and change depending on the situation, charging or not charging. So all those depend on semiconductors. Interesting area. If you want to dig into it a little better, that would be a great research topic if anyone's interested. Okay. Now, there is a table in your text, table 6.1, which lists your good conductors basically in the order of conduction. Silver, the very best conductor, which was also the top of the list for heat conduction. For the same reason, those free electrons. Copper next, gold next, aluminum next, graphite carbon next. Tungsten, not as good a conductor, but still conducts. Iron next, it's not a great conductor, but it does conduct. Lead next, nichrome, which is a nickel chromium alloy. Not a great conductor, but it does conduct. Okay? Does anyone know where you use nichrome? I think I'm pronouncing it right. Or nichrome. Nichrome. Nickel chromium alloy. That is, do any of you have electric range top? Or oven? That thing in the range top or in the oven that heats up and turns red, that's usually nichrome. Not a great conductor, so it produces a lot of heat when it does conduct, and that's what your filament is in your oven or your thing. They're just bigger than a filament. Okay? Now, your good insulators are lousy conductors. There are a few are listed here. Here's a few more. Rubber, certainly a good insulator. Glass, a good insulator. Carbon, diamond carbon, good insulator. Plastics are usually good, and wood is usually good, especially dry wood, not wet wood, or not sappy wood. Okay. So there, those are just all listed there, but the electrical conductors, they just listed metals. This listed a bit more. So let's look at the electric charge. What we've been talking about so far has been the microscopic scale, or basically submicroscopic scale, movement of electrons. And that's certainly what is moving. That is the charge that moves, is either electrons or ions, one or the other, usually electrons. Okay? But you don't see an electron, you can't feel an electron, you couldn't even feel the charge of an electron if you touch one, because electron is just way, way, way too tiny. So what we use for the macroscopic scale, something we can measure, is a coulomb. Named, because it's a capital C here, named after a person, Charles Coulomb, a French physicist who probably first identified this as a unit of charge. Now look how many electrons it takes to make 1 coulomb of charge. One that we can do. It takes 6.24 times 10 to the 18 electrons. That would be 6, 240, 0, 000, 000, 000, 000, 000. You'd have to have 16 zeros following your 624. And that's a huge number. and that is the metric unit of charge, a coulomb. Okay? Something you can measure, you can deal with on the macroscopic scale. Going the other way, the electron charge is a fundamental charge. You cannot get smaller than a single electron charge. Smallest seen in nature. The quantity of charge and the number of electrons are related to each other by this formula. The charge, Q in coulombs, is going to be the number of electrons times the electron charge. Okay? Depends on what you're measuring electron charge. If you're measuring it in coulombs, that would be how many coulombs you have. So you would need 6.24 times 10 to the 18 as the number of electrons times 1 electron charge to get 1 coulomb of charge. That's how that works. Okay? So going the other way, if you had 1 coulomb of charge and divide that by 6.24 times 10 to the 18 electrons, that gives each electron to be 1.60 times 10 to the minus 19 coulombs per electron. That would be 0.0000000000000000016, or something like that. Some incredibly tiny amount of coulombs per electron charge. Incredibly small number. But coulombs are things we can measure. Electrons, of course, we cannot. All right, now we get down. Whoa. We've now hit example 1. So let's go back to this and do example 1. Combing your hair, need to be clean hair, by the way, on a day with very low humidity, we don't have many of those here in the southeast, results in a comb with a negative charge on the order of 1. Ooh, let me get my pen back. First time I've written that. Yes, in this chapter. Okay. 1.00 times 10 to the minus 8 coulombs. That would be the charge on your comb on a dry day when you comb your hair. Doesn't sound like much, does it? So the question is, how many electrons were transferred from your hair to the comb? So that's the charge that you build up. That's 0.000000001. Okay, pretty small amount of charge. Okay, coulombs. How many electrons would that be? Well, we know from what we just said that multiply this by blank blank. Okay, the second blank we put electrons. I like to put a minus to remind myself it's negative charge per coulomb. Well, how many electrons per coulomb? 6.24 times 10 to the 18 electrons to make 1 coulomb of charge. So the coulombs cancel out, and that would give you 6.24, because 1 times 6.24 is 6.24, and then subtract that times 10 to the 10th electrons. That's how many electrons you combed off of your hair onto the thing to get that small amount of charge. Okay? That would be 624 that many electrons. There's thousands, millions, billions, 62,400,000,000 electrons you would have wiped off your hair onto the comb just to get that tiny, tiny amount of charge. Electrons are incredibly small. Incredibly small. Okay? So that's what they got. Let's see what they did. No, it's crazy. They said 6.25 is 6.24 times 10 to the 10th electrons. Okay? They use the other conversion and divided by 1.60 times 10 to the minus 14. So much easier to multiply. It's so much easier. Okay. That was example 1. All right, now we move to electrostatic forces. All right. How are we doing? Only got a half hour. We're going to make it. I hope so. All right, relationship giving force between two charges. Okay? What was the rule about like charges? What are they doing to each other?
They separate.
They repel each other. What about unlike charges? They attract each other. What's making them repel or attract? The forces between them. So this is the relationship between giving the force between two charges. Whether they're like charges or unlike charges, whether the force is repulsive force or attractive force. Very similar to Newton's law of gravitation, but there's a difference. Here's the formula. The force, electrostatic force, is equal to a proportionality constant because the force is proportional to the product of the charges and inversely proportional to the distance between them squared. Okay? Now, this constant of proportionality is K. Sometimes that's called Coulomb's constant. Other times it's just called the electrostatic constant. Now, it has units with it. The units have to be newtons because newtons are over here in force. And since you're dividing by distance squared, you have to have meters squared in the numerator. And you're multiplying by Coulomb squared, so per Coulomb squared in the denominator. So this Coulomb times that Coulomb cancels that out. The distance squared cancels that out, and you're left with newtons. Okay. Now, if you recall, well, let's see if they put it up here. I think they did. Yeah. Here is Newton's law of universal gravitation. When did you sneak in? I didn't see you. Not long, has it been? When did you come in? Just a few minutes ago? Okay, I was thinking. I didn't see you. Sorry. Calvin's here. Huh? I'm sorry? Oh, okay. I didn't see you. Sorry. Okay, so now we're only missing Austin, who should be in soon. Well, sometime. And DeAndre. That's all that we're missing. Well, except the people who have left now. We've been losing them faster than we've been gaining them, but they have been here at some point. Here's Newton's law of gravitation. The constant proportionality constant now is the universal gravitational constant, which is 6.67 times 10 to the minus 11 Newton. Now they got this wrong. This should be meter squared per Coulomb squared. So they have that wrong. That should be a meter squared here per kilogram squared. Okay? That's it for Newton's law of gravitational, the forces. And by the way, gravity is always an attractive force. Electrostatic forces can either be attractive or repulsive. We don't know of any gravitational forces that are repulsive. They're always attractive. Okay. Now, it's hard to compare these because the masses are measuring kilograms, which are huge amounts of mass, whereas the charge is a pretty small amount. Distance is still measured in meters, so it's hard to say, but look at the comparison between Coulomb's constant, 9.00 times 10 to the positive 9 Newton meter squared per Coulomb squared, compared to the gravitational constant, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Of course, kilograms are different sizes than coulombs, but still, it's a huge difference. So the ratio of those two is something on the order of 1.4 times 10 to the positive 20. Now what that tells you, basically, is the electrostatic forces are stronger than gravitational forces. Not by that much, but they still are stronger. But we've already talked about seeing the evidence of this. Remember when I talked about combing your hair on a dry day, clean hair, dry day, with a rubber comb, and then picking up little pieces of paper? Well, obviously, the electrostatic force pulling the paper up is stronger than gravitational forces trying to pull the paper down. So sure enough, electrostatic forces are stronger than gravitational forces. Now, this sounds counterintuitive, but it's true. but they don't go as far a distance. You have to get the poem really close to the paper before you'll pick it up. You can't hold it out here, whereas gravitational forces will act over the galaxy, or bigger than the galaxy. Gravitational forces go long, long distances, but are fairly weak. Electrostatic forces are much stronger, but go very short distances. Okay. Strange but true. All right. Now, before we go to force fields, let's do examples 2 and, no, just example 2. Electrons carry a negative electric charge, we know that, revolve around the nucleus of an atom, we know that, which carries a positive electric charge from the protons that are in the nucleus. The electron is held in orbit by the force of electrical attraction at a typical distance, so here is your D, okay, typical distance of 1.00 times 10 to the minus 10, pretty small distance, meters. Okay? What is the force of the electrical attraction between the electron and the proton? Well, if you go back to our, here is the force, K times Q1 times Q2 times D squared, divided by D squared. Here is your D. Okay. So the force is K times Q1 times Q2 divided by D. Now we're D squared, sorry. And we're just going to deal with the magnitude of the charge, not the sign of the charge. Okay? Well, if you remember what K is, 9.00 times 10 to the 9th Newton meter squared per Coulomb squared. So it's 9.00 times 10 to the 10th Newton meter squared per Coulomb squared. Times Q1. Well, one of these is a proton, one's the electron. They have the same charge, it's just different units. Different sign, but they have the same charge. So the Q1 is going to be 1.60 times 10 to the minus 19. That's Coulomb per, no, that's just Coulomb for an electron. But that's also the number for a proton as well. So that's your, get my pen back. Okay. That times 1.60 times 10 to the minus 19 coulombs. That's for the, one's for the proton, one's for the electron. Okay? And divided by the distance squared, 1.00 times 10 to the minus 10 meters squared. Okay? Nice to have a calculator that has scientific notation. If you don't have to have one, but it just makes the calculations a lot nicer. Okay, so if someone will calculate with me and see what you get. Now, you know how to do scientific notation on the calculator? You do not do times 10. Do not do times 10. You type in this number, 9, you don't have to put the 0.00, then EE or EXP. And then you get a little number, that's where you type in the 10. So 9 EE or EXP 10 times 1.6 EE or EXP minus 19. Now for the minus 19, be sure you use the minus that's in parentheses, not the subtraction minus. That's going to try to subtract something. This is your negation key. Okay. EE or EXP, the negation key minus 19 times 1.6 EE or EXP, the negation key in parentheses, minus 19, divided by 1 EE or EXP minus 10, Oh, you need to back off. Open a parentheses, 1 EE or EXP minus 10. Close parentheses, square that, the squaring key, and then press equal. Wow. Okay. A lot of activity there. What do you get? Anyone got an answer yet? I'll walk through it with you again. You got something? Oh. 9 EE or EXP 10 times 1.6 EE or EXP minus 19, be sure you use the minus in parentheses there, times 1.6 EE or EXP minus 19 divided by, open parentheses, 1 EE or EXP minus 10, close parentheses, and find your squaring key, the x squared key. Press that one, then press equal. See what you get.
So square root at the last.
What's that?
Square at the last.
Yeah, you square, you open parentheses, type in 1 EE EXP minus 10, close parentheses, square, then hit equal.
I got it.
What?
7.
Huh?
7.7.
No, I don't think so. It should be 2.3. Did anyone else do it?
I probably did wrong.
Okay. Okay. I'm going to write 2.30 because the book said it. I don't know if that's true or not. I think it probably is. Now let's look. Times 10. Now here you had times 10, but there you had minus 38. So that would be minus 28 divided by a minus 20. So that should be about minus 8. Minus 8. Now let's look at the units. Coulombs times coulombs, coulombs, those cancel out. Meter squared cancel out. So that leaves you newtons. Now that's a pretty small force, okay, until you think about how incredibly tiny the electrons and protons are. It's really a pretty big force. Amazing, okay? So 2.30 times 10 to the minus 8 newtons. All right. So now let's go to force fields. How do forces travel through space? We know gravity does because the sun is pulling us to it. You know, that's what keeps us in orbit around the sun. The moon is kept in orbit around the earth because of gravity. It goes through space. Well, same thing about charges. If I have a positive charge here, a negative charge there, they're going to be attracted because it goes through space. How does it do it? Well, we kind of make up this abstract concept here called force fields, and it seems to work. How do forces act through space? Charges are surrounded by what we call electric fields. Okay? Now, these are vector fields. Remember when we talked about vectors? Vectors have magnitude and direction. The magnitude is the strength of the field. The direction is which way they're pointing. The fields and the charges are inseparable. If you have a small positive charge up here, there's a field around it. You can't have a charge without a field. Okay? If you have a field, there's got to be a charge. Okay? They're completely separate. Or electric field anyway. Okay? Fields act on other charges. So if you had a small positive charge here, bring in another positive charge here, it's going to try to get out of there because the fields are acting on it. But if this was a negative charge and you bring in a small positive charge, it's going to be attracted to it. You have to hold it back to keep it from colliding. Okay? So fields act on other charges. The direction of the field equals the motion of the positive test charge in the field. There's the key. We visualize it with lines of force. Now, the same ideas apply to gravity and magnetism. The only difference is gravity is always attractive, but electricity and magnetism could either be repulsive or attractive. That's the only difference. Okay? Now, here's how we picture this. What if we had a negative charge up here somewhere? Just some sort of negative charge. Bring in a small positive test charge. That's always what we use to start with. Which way is it going to head? Which way do positive charges go toward around negative charges? To them, yeah, moving closer. So around the negative charge, the force fields are always pointing to a negative charge. However, if you had a positive charge up here, and you bring in a small positive test charge, which way is it going to do? It's going to repel. Okay? So therefore, positive charges always have the force field pointing away. So the force field always points away from positive charges and toward negative charges. Always. Electric field lines point away from positive charges and toward negative charges. And we draw them by lines of forces, which are these vector magnitudes and directions. Okay? Now, we'll see the same thing later with magnetic fields as well. Okay. There should be a couple of things here they're not showing. Here we finally get one. Okay. Okay. They're in reverse order from what they are in the book. If you have two, and it may be hard to see from where you are, but it's in the book. I think these are both positive charges here. Yes, they are. How do I know? Because the arrows are pointing away from them. And the arrows are pointing away from this one. So these are positive charges. These are the lines of force, or the force fields. And you try to bring them together because these are pointing away from each other. They are pushing them apart. They're bending the force line because these force fields can never cross. They can join, but they can't ever cross. So therefore, they bend away, and they're acting like springs, pushing each other away. So like charges repel each other, and that's why. Because the force fields are pushing them apart. Because the force lines can't interact when they're both going in the same direction, so they push apart. Whereas, if you have a positive and a negative, here's the positive, there's the negative. It's always pointing away from the positive charges, but pointing toward the negative charges. Hey, these fit perfectly, okay? So they actually pull them toward each other because the force fields connect and tend to pull them closer and closer together. So this is why unlike charges attract each other. These are the field lines around an unlike charge. Again, just imagine this one is there. Positive charges, the field lines are always pointing away, and negative charges are always pointing toward. They connect here and pull them closer and closer together. Whereas like charges push further and further apart. If you had two negatives, they would be just like the two positives. The only difference is these arrows would always be pointing inward, and again, they try to push each other apart. Make sense? Okay. Now, that leads to another concept. And this concept is that of electric potential. Okay? Let's go over the meanings here. Boy, this is going to be close. Electric potential is a scalar field, not a vector field, a scalar field associated with potential energy. Because if you think about it, forces are vector quantities. Energy is a scalar quantity. There is no direction with energy. So therefore, these are scalar fields associated with potential energy. The unit for electric potential is your volt. Why is it capital V? Named after Alexander Volta. He was Italian who did some of the very earliest work with electric potential. Built many of the early batteries, Volta. He was in Lake Como, Italy, Italy, which is way up, real close to Switzerland. And my wife had meetings there one summer at the week in between our terms, either between summer and fall, spring and summer, or summer and fall. I don't remember which. I think it was between spring and summer. And so I got to go, and her niece got to go with us too. And while she was at meetings, her niece and I walked around town and enjoyed the scenes. And we saw this really beautiful building over here. We went over to see what it was. It was a monument to Alessandro Volta. That's where he was. That's where he worked. And many of his early batteries were there in that museum. Okay, really beautiful. But anyway, Alessandro Volta, the vault's named after him. It's related to the work involved with positioning charges. If you had a positive charge here, you tried to bring another positive charge, you're having to do work to position that close to that, because they're trying to repel each other. You're doing work to position it there. Or if you have a positive charge here, you're trying to bring a negative charge in, you're having to do work keeping it from colliding with it. Okay? So you're related to the work involved with positioning the charges. The potential difference, now if you think back when we did potential energy in the lab down there, it was how much the difference was, the change of height. That was your potential difference between gravitational potential here and gravitational potential there. The difference in the height. Well, here's the difference in moving charges. The potential difference is important in producing forces and moving charges. What difference do you have in those electrical potentials? It's analogous to moving masses in the gravitational field, like I just talked about. Okay? So here we have a fixed 1 coulomb positive charge. Say it's standing on a stand here, and I'm bringing one in from the outside. I'm having to do, if this is 1 coulomb, that's 1 coulomb, I'm having to do 1 joule of work to bring those two charges 1 meter closer to each other, because the force is, related to the electrostatic constant times charge times charge divided by distance. So 1 coulomb of charge bringing close to 1 coulomb of charge, 1 meter, that would be 1 joule of work. That's your potential. And the volt is defined to be 1 joule per coulomb. Joule per coulomb, the amount of energy per unit charge. That's what a volt is. Energy per charge. So there we have it. Volt is energy per charge, and this would be work in joules divided by charge in coulombs. Now, here's the interesting thing, folks. Hopefully it's not confusing. The parameter for voltage is V. The unit for volts is also V. Okay. The parameter for work is W. The unit is joules. The parameter for charge is Q. This unit is coulomb, capital C. The parameter for voltage is V. The unit for volt is V. That's the one that has the same one.
Q means.
Huh?
Q. What that means on that? I can't see.
Q means charge.
All right.
The amount of charge. And it's measured in the unit of capital C coulombs. Okay. So that's how we define a volt. The work done per unit charge. Joules per coulomb. All right. Oh, did you need that longer? Oh, okay. Right. All right. Now we're moving toward electric current. All right. If we can get this done in the next 10 minutes, we'll be ready for lab. Okay. Electric current. Earlier, we talked about electrostatics. Static charge that was stationary. It goes to an object, it stays on the object. If you touch it, you get shocked. Okay? Now we're talking about moving charge. With electrostatics, the charges are more or less fixed in place. Now we're allowing the charge to move, meaning we have conductors, and now we're talking about electric current, the flow of charge. Now, unfortunately, most of the time, this charge flow, they're electrons. Occasionally, there are ions, but most of the time, they're electrons. Okay? And that's where a little bit of a problem occurs, because electrons are negatively charged, So they go in the opposite direction of what we would think they would. The reason for the charge flow, you have a potential difference or a voltage. You have different energy levels per unit charge, and that makes the charges move according to that voltage. What an electric circuit is then is the structure is designed to, I don't like these terms, localize and utilize currents. In other words, to identify and direct where they're going and to use the currents for whatever purpose. So that's what electric current is. And let's look at what we mean by electric circuit. This is at the top of page 148. Your structure here, you have to have something to give energy to the charges. That's your voltage source. That's your energy input. If you don't have that, you just have a circuit. Nothing's happening. It's necessary for continuing the flow. You have to have something pumping up the energy. The circuit elements are then things that produce heat, like if it was a space heater, it would be light if it's a light bulb, it would be a paddle wheel if it's work being done, whatever it happens to be. Okay? Now here's the current flow convention. This is what gets a little squirrely. The current flow, like everything in physics, always moves from high potential to low potential through an external circuit. The trouble is your high potential, the plus charge of your battery, say, electrons move in the opposite direction because they go away from the negative charge toward the positive. Your conventional current is going away from high potential to low potential. So you have two different types of flow. Conventional flow, which would be where positive charges were, if you had positive charges, most of the times we don't, or the electron current, which goes from negative to positive because the electrons have to be negatively charged. Now there is a water pump analogy, which is a pretty good analogy. Let's just see what that is like. Here's your voltage source. Okay. Now, notice they're not telling you which is which is positive and which is negative, which is almost good. Okay. If this was indeed your positive charge here, positive pole of the battery here, and that's the negative pole of the battery, this would be your conventional current, going from high potential to low potential. If, however, this is electric current, electron current, then this would be your negative, and that would be the positive, because electrons flow away from the negative, negative toward the positive. So, fortunately, they didn't identify, we're just showing you the conduction here. This provides energy to the charges move. Here, the energy is used because you're using to light the light bulb. If that's a filament, incandescent filament, you're heating that hot enough to make it glow. So you're producing heat and light. So you're using the energy here that the battery supplied. You're not using the charge. You're not using up charge. You can't use up charge. Charge is conserved. What you're using is the energy that the battery supplied to the charge to produce the light, and then the charge comes back to the battery, gets pumped up again, and goes back out again. Okay? Here is the water analogy. Your pump is what pushes the water up to the higher reservoir, upper reservoir, because it's pumping the water. It's giving gravitational potential energy to the water. Okay? Then from here, the water falls down under its own weight and turns the paddle wheel, which is like your light bulb. That's the load. That's what's making the energy. That's, could be producing electrical energy. Whatever it's doing, that's the load, and then the water goes back into the pump and gets pumped again. Now, there is a breakdown in the analogy. There always is an analogy. If you were to cut the wire here, you lose the flow. No flow. Electrons don't come spilling out of the wire. If you break the pipe here, that's exactly what happens. The water, which is analogous to the electron flow, the water comes spilling out and you lose everything. So the analogy does break down, but the basic principle is still there. Okay? Now, what is the nature of current? This is what we were talking about. Remember this. will be doing this in lab today, okay, which is only a few minutes away. If you identify the positive pole of the battery here and the negative pole here, this is conventional current moving in this way. It flows in that direction, from positive to negative. However, the electron flow, or current, goes from negative to positive because electrons are negatively charged. They go in the opposite direction than the conventional current, which would be the movement of positive charge if you have one. In both cases, the charge is being given energy by the battery, and it's using the energy in the load, and the load is where the action is going on, producing light, producing heat, producing whatever. Okay? So historically, the nature of electric fluid was unknown. So somebody, I think it was Benjamin Franklin, said, well, let's just name an electron negative and the proton positive. Sounded reasonable. Okay, it turned out it was really backwards. We really should have done it the other way. Everything would have made more sense. Okay, but it's that way. The current is thought to be the flow of positive charge in the conventional current. We know in reality it's a lot more complicated. And it's not always the movement of electrons. In the battery, it's the movement of ions. This whole ions in solution, because this battery has a solution of sulfuric acid in it. You don't want to spill that on your clothes, otherwise you have holy clothes. You can wear them on Sunday. No, I'm just kidding. Okay, but that's what's moving in here. In an alternating current, it's not a continuous flow. It's going back and forth, back and forth, back and forth. So you don't even have any kind of direct flow like this. Okay, it's just the movement of charge. Okay, so opposite direction in electron flow. Now, the next thing here is current mechanisms. And I think this is what they call in your book the nature of current. It's a little before that, actually. No, yeah. Let's hit this slide because we need to get down to nature of current. But we don't need to get to resistance. Yeah. It's going to take us just a little bit longer, but it hopefully won't be too much longer. So we're going to stop before resistance. Okay, we've already hit this, the nature of current. Okay, here, current mechanisms. In liquids and gases, both positive and negative charges move. Generally, they're ions. Positive ions moving one way, negative in the other. Now, when they say liquids and gases, the liquid, like in the battery acid, the charges are moving both directions. Negative ions are moving to the negative pole, and positive ions are moving to the positive pole. There are ions moving. Okay? In gases or in plasma, it's positive and negative ions are moving up there, like in those tubes. We talked about that before. So in liquids and gases, generally you're talking about both positive and negative ions are moving, charges are moving. In metals, it's the free electrons. And that's what we usually deal with, and those are always generally negative in charge. You can think of this as an electron gas somewhat, but guess what, folks? It's not really the movement of charge. It kind of is, but it's really the change in the field. Okay? Because when there is no field there, the electrons are just really all mixed in there, just hanging around. They're not really moving. They're always moving, but they're not net moving. Once you introduce a field, now suddenly the electrons start moving, okay? And the electrons tend to move in the opposite direction of the field Because remember, the field points the way a positive charge would go, so they move this way. Do they move very fast? When you flick the light switch, do those electrons immediately go to the light? No, it takes many minutes. Well, this is alternating current. They never get there. They just go back and forth, back and forth, back and forth. So in reality, but even if that was a battery, it takes a long time for the charge to move in a wire. The field is almost instantaneous. You flick the switch, the lights come on immediately, almost immediately. Because the field is set up, that's what's really doing the job. So it really doesn't matter what charges are moving what direction. It's the field that matters. And it's instantaneous because the electrons that are right there near the switch, they feel the field at the very same moment the electrons right here next to the light bulb feel it. The field is set up immediately throughout the whole circuit, and then they start moving. It's the movement of these charges, not the ones near the switch, that actually get the light to come on. Okay? Because the field is instantaneous. Okay? So we think of it as electron gas. It really isn't much. The drift velocity of electrons is incredibly slow. We'll see an example later in the chapter. The electric field moves at nearly the speed of light. Not quite, but close to it. Okay? So the drift velocity of electrons is incredibly slow. The field moves almost the speed of light. So in an alternating current circuit, it's the field going back and forth, back and forth. Not necessarily the electrons, it's the field. Okay? The electrons are being affected by it. Okay? So, what are we talking about? With the movement of charge, that's called current. And the symbol for current is capital I. This is the parameter. And I is Q, which is charge over time. Charge per unit time. Coulombs per second. What's the unit for current? Amps. Why is it? Yeah. And why is it a capital A? Named after Louis Ampere. Another French. The French were really on top of much of the development of electricity. We had Volta from Italy. Galvani was from Italy, who first discovered a battery, but his was a mistake almost. But Coulomb and Ampere were from France. The next guy we'll talk about, Ohm, was from Germany. So it was all over Europe, but France was a lot of it. And guess where Benjamin Franklin was at one time? Ambassador to France, about the same time that these guys were there. So you know they got together. Okay? So the unit for current is ampere, capitalized, also named after Louis Ampere, sometimes abbreviated amps. Okay? Charge per unit time, current per unit time. This is current. Charge per unit time, that's what current is. And we talked about direct current, where the charges typically move in one direction. They're being bounced all over the place, but overall movement in one direction. Most of your electronic devices, anything that has a battery, solar cell, anything that has something like this. This is alternating current because that's plugged into the wall, goes through a converter here and becomes direct current. Computers, iPhones, she's got hers plugged in there. Look at that box that she has. That is what changes the alternating current to direct current. What's your car? AC or DC?
DC.
It's DC. Just about everything in your car is direct current, except your generator.
Right.
And that's making DC, making alternating current, but then it's converted by a, they used to call it the alternator. Now I think, is it still called alternator? But anyway, that's what converts it back to DC. Because if you were trying to recharge the battery with alternating current, be charging, discharging, 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 would never get anywhere. But you change it to DC, and now it can charge the battery. It's a pulse charge, but it is a charge. Okay. So the DC is anything that has batteries. Alternating current is basically anything that plugs into the wall. Okay. The charge motion is oscillatory, no net current flow. So who cares whether you talk about electron flow or thing? It's electrons moving back and forth pretty much, but it's immaterial. then we'll pick up next time with resistance. Okay? All right, that gets us to page 151. That's a good place to break. And why don't I go on and pass out your lab to you? And you can be reading on the lab. And I don't know if there's going to be people in this lab here or not. If they're not, we'll be in 253. If there are people in there, we'll move across the hall to 252. If there are people in both labs, we'll go down to 259. If they're there, we may come here. Okay, but I think they'll be in one of those things here. So, let me pass out the to you. We barely got it covered. There are some things on this lab we haven't talked about yet. I'll try to explain them to you as we get closer. Okay? Three I'm going to do here. Okay. That's one more. That's one more. One more. Yeah, all right. My distributor here. Okay. Oh. All right. Find the lab. It's going to take me a few minutes to get broken down and set back up again. So, yes. Oh, you want that one now?
Yeah, I missed like 2 or 3.
What's that?
I missed like 2 or 3 labs I got to get.
Okay.
Yeah, I know. I'm taking tennis.
Okay.
Yeah, so you said I'm mistaken. You ain't even
Okay.
making jokes like this.
What do you say?
You just don't like that.
What's that?
No?
Okay, I'm getting to that. Okay. I think y'all were both here for working power when we did the steps.
I don't know. Let's see.
You were up and down the steps.
I missed the last 3
We had the
ones.
steps.
Yeah,
you
I
did the steps.
Yeah.
Okay.
I think that was
Okay.
last
Especially
one.
Thursdays.
The one with the pendulum,
Yes, sir.
I didn't
Pendulum,
do
that's
that
Thursday.
you weren't there for that one? You were, weren't you? Or weren't you?
Was that Thursday?
No, this was back.
I missed the past 3 ones.
This is 2 chapters ago.
No, I think I've got
There was
everything.
one page, and then you,
Oh, okay, I did do that one.
you did that.
Yes, sir.
I
Yeah.
thought you
That
did.
was the one we did. It's like
We thought it was
picture.
That's about, huh?
you just showed.
Okay.
Yeah.
You did here and here and here, and then later we exchanged data and you did in the margin.
Yeah.
We're giving
Were
this
you
one
there for
minutes.
that one?
And
Okay.
this time we had what we had cord, the string, whatever, when we was in their room.
Yeah, that's the one. I think.
Yeah. Okay. All right. Hold on, I got to get back to where I was. Okay. Then we had the 2 labs on thermometry. Heat
He
temperature.
missed
I
that.
missed.
You
that
missed the first one. You were here for that one, right? Okay.
Cool.
Now, the last one that we did Thursday, that was thermal energy. Okay, one of these is printed front and back. The others are stapled.
Yes, sir.
And then did we do one?
This is the one we did last Thursday.
You want Tuesday? Is that one from last Tuesday?
Tuesday was the first one, the
This
thermometry. That was
No.
Tuesday, that was Thursday. No, wait, yeah, that's right, yeah.
Do you have the Thursday from the one before that?
Okay,
Sorry,
that
I
was
was
one,
I was out a few days.
yeah. Well,
I hate doing
the
makeup
one
work.
before that was that one I just did. I thought you said you had it. It's the
Oh,
energy
cool.
one like this. Okay, we started with, we had a big mass on a pendulum, and we raised it up on a meter stick, and we were doing calculations.
Okay, I guess I didn't do that one. Then.
Okay.
I thought you were talking
That
about the
one, you
we
pulled it
had
out,
last year.
yeah. We did 2 down there,
Okay, I only did the first one.
the first one, okay.
That's what it was.
Okay, let me make sure that's the previous one to that.
Yeah, this doesn't look familiar. Or this doesn't. I didn't do this one. And then I need to make up. I know I'm giving you a headache, but I need to make up that test also. Could I make that up later on today or Thursday?
Probably,
Or something?
if we have time today, you can do it, or you can do it Thursday, either one.
It probably shouldn't take me a minute. I'm usually pretty quick
Yeah.
with the test.
Okay,
Thank you.
All right, glad to. Okay. What's that? Yeah, the initial. Okay? Well, that's before we get going. I know y'all, while you've been waiting, we're reading the lab. Very good of you to do. Okay? Oh, yes.
Yeah, I'm summarizing it.
All right. So I know y'all were reading the lab, so you understand these symbols.
Yes.
Okay? Your batteries are usually written as a series of short lines, long lines, short lines, long lines. The last long line is the positive side. The first short line, or whichever way it's placed, is the negative side. Okay? As shown here. Okay, we're not going to be dealing with grounds because we're dealing with DC circuitry, so we're not worried with grounds. Go down to the second one, and you see resistance are these jagged lines. If you put a circle around the resistance, that indicates the resistance is the bulb, which is what we've got. So that's what ours will look like. We're not going to deal with variable resistors, so don't worry about that. We're not going to deal with open and closed switches, so don't worry with that. We're not going to worry about wires crossing but not joining, or wires joined. We're not going to deal with that. What we are going to start with is the illustration, and this is procedure 1 on page 179, but it's the picture on 180. Now, there are a couple pictures on 180. Well, one picture, one diagram at the bottom, and a blank. So we're going to deal with the blank. Okay? The box that's inside the dotted lines here. Everybody see? Okay. Now what we're going to do there, don't worry about one flashlight battery, one flashlight bulb, and one 10-piece. Don't worry about that. What I want you to do in that block there, top of the page, is the rectangular block that is the dotted line. I want you to draw the circuit in number 1 below it. You don't have to worry with the switch. You can just draw a straight line through there, but draw that circuit with a battery, a bulb, which is a resistor, and then the rest, just do it. You don't have to put a switch in it.
Size or big?
Huh?
A big one or just
Number 1. Do circuit 1.
Right.
Draw it in that above.
I said small. You want a small or big?
Well, you've got a block there. Use as much or as little as the block as you want to use. I've got to be able to read what you're trying to show me. Okay?
I ain't no artist.
Well, it's pretty simple. Okay? Now, you notice your battery has a long line and a short line. So be sure you do something like that because I have to know which is the plus and which is the minus. Okay? So there's your sketch of a circuit. Number 1. Okay? The way you have it drawn, your battery has a long line and short line, right?
Yes.
Okay? The way you have it drawn then, I want you to show the direction, the flow of conventional current. Remember when we did that on the slide set today, I said, you're going to do this in lab today. So I hope you're paying attention. If you got your book, you can probably find it in the book. If you want to borrow my book, you can borrow my book. Okay? Draw one arrow that shows conventional current, another arrow showing the electron current. Okay? Just like it was in the text today. It was on the slide. I said, we're going to do this in lab today. And of course you were paying attention and you took note of it. Right?
Yes.
Of course. If you have any questions, ask me. Let's not get it wrong, but ask me if you got questions. Anyone need my book?
Yeah.
You do. Okay?
I need your book. Make sure I'm right.
Yeah, you're supposed to be putting an arrow on there showing. You want me to find the page for you too?
Yeah. To make sure.
Okay.
Just checking it. Because I know it's arrows.
But that shows the battery.
Yeah,
and,
because you said negative,
yeah.
positive this way, and then negative, positive, negative, the positive, negative, the positive this way though.
Okay, well, whatever. That's the one. Okay. If you have any questions, ask me. You got it?
Yeah.
Don't lose my papers or my CD from the book. Any questions? You got it? Understood? You got it? No questions. All right, good deal then. That's the first thing. Procedure 1, draw your circuit and label conventional current one way, electron current the other. All right. Now, the second, procedure 2, notice the construction of a flash bulb light. Or it says flash bulb. It's flashlight bulb. That's all. I couldn't read it. Okay. Now I'm going to hold up this one. You may not be able to see it, but this is a little bit, that's a bigger picture, but this gives you an actual three-dimensional. Okay? Now what we've got with the bulb, flashlight bulb or whatever bulb it is, notice at the end there's a terminal here. This is what makes contact. It's surrounded by a black plastic, which is a non-conductor, an insulator. And then you have the exterior, which is metal again. So you have metal at the tip, and you have metal on the sides, but you have black plastic insulator in between. You can't see where it's heading, but one of these is connected to one side of the filament, and the other is connected to the other side. This picture that you have here is incomplete, because the filament's sitting there with no connection anywhere. So you need to draw 2 lines on this. One to go one direction and one the other. Okay? You understand where you need to draw it?
Yes, to each black mark, just bring it down.
Okay? Well, where do they go to?
Down there. Okay. Either, I mean, there's 2 different light bulbs. Either they go right there, and then to the side.
You're drawing on my picture.
Yeah, I just did it.
Okay, do it on yours. Okay?
You want it like that, or do you want
Okay,
one
now
down
you got it.
there and then one to the side?
That, okay, this is going through the insulator. That's not going to do any good. That is where,
My light bulb's different.
yeah, your light bulbs is off too.
Yeah, they are.
Okay.
What are we supposed to be
I can
doing?
tell.
Yeah.
Huh?
What are we supposed to be doing now?
You draw 2 lines to make that complete, so it works. This one right here. Okay? This bulb. Well, that won't come on, will it?
No.
Why? There's no connection. This goes somewhere and that goes somewhere. Where do they go?
They're supposed to go, these 2 things should be right here. The
Where?
resistor. It's on power.
That ain't a good picture.
One goes where?
One go right here.
Where?
Right here.
Okay, that's the insulator. You don't want to draw.
One is resistors.
No, that's not a resistor. That's the screw in of the bulb.
Oh.
That's the threads in the bulb. Okay? I was just describing this. Okay?
Okay, you scrap.
Here's metal here. That has to make contact with one side of the circuit. That metal there makes contact with the other. So what must be going on inside here? One of these goes to that, and one goes to that.
Can you show us how this thing works?
Right here.
No, that's glass there. Go down to
Oh, yeah, right here. And then
Okay.
the other one go all the way over right here.
no, it doesn't go outside. It's all inside
Oh, well. Go right here, then.
to the tip. Very good.
How does this thing
Okay.
work, boss?
Say again?
How's that box there work? How we cut it on the yard?
She said, how do
I'll explain that in a
we
minute.
power?
Okay?
Obviously,
When the light bulb
we're
comes
just
on.
gonna hang it
Okay?
together, everybody. Let's
All right.
get this squared away.
Okay, are there any
Yeah,
questions?
I got it now.
Okay. Doesn't go outside.
They're outside, but
It's all interior. Yeah. Be fine.
you don't say nothing. You don't like be right there. Right here, and then one.
Sure, you know something like that, Caleb.
Alright, we got it.
Everybody
Sure,
understood?
you know that already.
Any questions? Okay. So that's number 2. Okay. Now the rest of them are going to be done on your box here.
Yeah.
I think I got this out of your box, so I'm going to put it back up. Any questions?
What's next?
Okay. Now, I've wired number 1 on each one of your boxes here. Okay? You're welcome. Anytime. Okay. Now what we're going to do is, let me explain first what we're doing, and then I'll tell you specifics. Okay, what we're going to do is wire the circuits, and you're going to do the rest of them. I've got the first one wired for you.
Yep.
What we're going to do is, okay, the one you got now, you're going to turn on the power supply.
Turn on
Like
the
your
red
battery.
button. Good.
That's the little red switch.
He just wants to wire up all these.
Okay.
What are we supposed to be doing?
The red switch, upper right corner. That's the on-off switch. Okay? Push it in.
That's the switch. Okay.
Okay, push it back.
No,
Push
that's
it in,
switch.
get it
That's
off.
off and
Okay?
on.
That's going to turn it on or off. The knob over here on the lower left corner, right above where the wire's attached, that's going to adjust the voltage.
Yeah.
You be very slow and careful with adjusting the voltage. Okay? Looking at your light bulb as you go.
If you go fast, you're going to blow.
You'll blow your bulb out,
Yeah.
and you'll overheat the wire,
Overheat the wire.
and you're putting on my wire for water. Okay. Now, what I want you to do, okay, listen first. Folks, please, listen first. Okay? So what you're going to do is set up the circuits. I've done the first one. Okay? Let's turn them off for now.
Turn off.
Okay. You're going to set up the circuits, and then you're going to fill in the table number on page 183. This table goes first. You got a question? Oh, okay. Yeah, I don't mind. I understand what you're doing, blocking them. Yeah. Wish we had a screen. Okay. Now, okay. So what we do, you're going to fill in the, you got a copy of the lab, right? Okay, good. You're going to fill in the information in the table on page 183. And here's the two pieces of information in general that you're going to put in the table. Okay? Now this first one, okay. Let's go back and read what we're going to do on number 1.
Yeah, directions.
Page 181, using the brightness of the bulb from sample circuit 1, that's what we've got set up, sample circuit 1, to be the normal, describe which circuits have bulbs with normal brightness, which ones are dimmer, and which ones are brighter. So one of the things you're going to put in this block here, under observation, is brightness. Okay?
How can you tell that?
Say again?
How can you tell the brightness?
I'm going to explain that. Okay? Okay? You ready? You're going to put either normal brightness, dimmer, or brighter. One of the three. You may have one of these, you might just put doesn't come on, which would be dimmer, but you can write does not come on, if that's the case. So it's either going to be standard brightness, brighter, dimmer, or not coming on. So one of 4 choices. That's going to be one observation. The second observation you're going to make, if there's 2 bulbs in the circuit, and this one only has 1, if you have 2 bulbs in the circuit, then you're going to remove one and tell what happens to the other. Either it stays on or it goes off. Right? So that's going to be your second observation. When you remove a bulb, either this other bulb stays on or goes off. Understood? So those 2 observations, if you got 2 bulbs, you'll make in each one. Now this first one, you might also put your standard voltage. The voltage you decide is your standard brightness. Okay? So what I want you to do now is turn on your power supply, push a little button, and your thing should read something awfully close to 0, right? Now very slowly start increasing the voltage until you see the bulb get what you considered a standard brightness. If you get too bright, I'm going to scream at you, okay? So go very slowly until you get what you consider a standard brightness. Okay, let me take a look. That's a little on the dull side, so turn it a little bit more. Okay, look. That looks pretty good, doesn't it? Are you doing that, or is it doing it? Okay. Whoa. That's a little on the bright side. Turn it down just a little. Huh?
Is that too
That looks like a good standard bright. That looks pretty good. That's too bright. Turn it down. Turn it down.
It's not gonna be long.
Oh. Okay.
You gonna bust your
Maybe
fingers
a
off
little
this rock.
Okay. All right. Now everybody take a look
I'm standing
and
bright.
see that's your standard brightness.
Yeah.
You're going to compare everything else to that brightness. Okay?
Yeah.
So you can write under your observation for number 1, standard brightness, and go on and put down what voltage you are at that brightness.
We at 4.5.
Okay? Whatever you are. Okay?
Yeah.
Okay? That's your standard brightness.
How we gonna know that when it stay on or off?
Say again? Say again?
When we gonna know when it's staying on and off? Right?
I don't know what you're saying.
When
Okay,
it's
that,
staying-
no, you're going, okay. If the bulb doesn't come on, then it's off. Okay? It's either, just notice that. Now turn it off. I don't want to burn out the battery, the bulb. So you already turned it off? Huh?
You said 2 observations there.
Okay, good. All right. Now, I do want to point something else out to you before you get going too much here. Okay. That looks pretty good, except where was this plugged in before? Right there. You see, here's the circuit. It goes from this pin to that pin. So if you put this one up here, it's not going to down.
It's gonna take a minute.
Down here. Okay. No, that does, but this shows here where the circuit is. There's the lamp. Okay. Right there. That's 2 bulbs in series. Okay?
Series is
2 bulbs in series. Now wait. Okay.
series on
Where did you
the
unplug? Where did you unplug them? Why did you unplug both of them? These are red. Okay. So just back where it was. Okay, let me get this plugged in.
The series
Where
supposed to be
where was that? Okay, it was there. So obviously the current is going through here, just like the line says, right?
right.
You can actually see where the soldered are. So then, if you want it in series, you put that one, flip it over. Okay.
How do we do 2
You
batteries?
put that. So this one is with that.
This
This one.
says 2 batteries in series.
You see, that makes a series circuit. You see?
It's
Okay.
equal to.
And then you put that right there.
I feel it.
Okay.
I got you.
Okay. Follow the line. Okay.
I
See that one there?
You know.
Put that up
I do
there.
again. See the move, you know.
That's right. There we go. So you see now. By the way, we haven't talked about in class. We haven't talked about in class. I didn't turn it on yet, did I?
How do we do 2 series?
That's
How
a
do we
great
do 2 batteries in series?
Say again?
How do we do 2 batteries in series?
Okay.
I was trying to
get to
figure
that.
out.
Okay? All right. Now here's the thing we didn't get to talk about in class. It comes up later, but the lab came now. The difference between series and parallel. The series, the current goes through every device on there. Okay? One complete
Each load.
pathway.
Yeah, each
One
pathway.
complete pathway. Okay? When we're talking about parallel, which is going to be next, you actually have 2 pathways, and it's shown in your illustration. And we'll get there. This are 2 bulbs in series. Okay? Now, when you turned off your device, you didn't change your current, did you? Your voltage, did you? Okay? So when you turn it back on, it'll be the same voltage as before, right? Now, let's take a look at our picture, our diagram for number 2. Notice number 2 is the same voltage as number 1, right? One little line, one big line, right? Okay? Are you paying attention?
I'm putting it
Okay? So when you turn it back on, it should be at the same voltage. Turn it on and see if you got the same voltage as you had before. Okay, that's all right. That's right.
Yeah.
What did you have before?
Yeah.
No! Leave it where it was before. I said, don't change the voltage. That was brighter than it was before. What did you say the voltage was? Well, then put it at 4.5. You have to be really slow and okay. That's probably close to that. That's your standard voltage, right? Okay. All right. Now, what two observations do you make? Okay. Number one, you said dimmer. Okay. You're making that comparison to the standard. And number two, okay, put your circuit in. Okay. Okay. What two observations do you make?
The voltage got split in half.
You got dimmer.
Okay.
You got dense.
Okay, they both went dimmer. Right? That's one.
If you go from
These are
standard
not
brightness to
dimmer,
dim,
bright
you'll
as
be
standard.
dimmer.
Okay. Say again.
We just go from standard brightness to dim. That's okay.
Okay, that's it. Well, what's the second observation?
If they stay on it, both of them.
Remember I said it?
Remove one. And
Yeah,
stick
what
one and
happens
stay
if you remove one bulb? Remove one. What happens? The other one goes, either stays on or goes off.
What am I supposed to do?
What happens to the other?
It turns off.
Turns off. So that's your second. First observation, is it standard, brighter, or dimmer, or goes all the way off? And the second observation, what happens when you remove one bulb? What happens to the other bulb? Okay? As soon as you finish that observation, turn it off.
Was the
Yeah.
voltage supposed to go down?
It might a little bit.
Okay. Ours just went down. Like, when
Okay, it does some because, okay. It's okay. But turn it off. Okay? Now, what are you doing now? Okay, you're not supposed to be taking voltage. Okay. All right. Now you get to set up, if you're paying attention, set up circuit number 3. What do you notice about 3?
Two batteries in one.
Okay. Now it shows twice the battery cells. Now here's what I do not want you to do. I do not want you to double your voltage.
Okay.
We might blow out the bulb. Well, how many bulbs you got in there?
Two.
One.
One.
Look at number 3.
Oh.
Okay? So, put one bulb back in, just like circuit 1 was. But I do not want you to double the voltage. Okay, plug it in just like number 1 was. Okay? And what I want you to do is gradually increase the voltage until you see a change in the bulb.
I'm going to increase it now. You see it increase?
It increases. As soon as you see it increases, shut it down. Turn it off. Okay, did it get brighter? Yay or no?
Yeah.
Okay, that's your first observation.
You got
Standard, brighter, or dimmer?
Right there.
Okay, I didn't want you to double it. Okay, as soon as you make an observation, turn it off.
I did.
Turn off the button. Okay.
Right there.
All right. Okay, did you make your observations?
Yes.
There was only one bulb, so you don't have to remove a bulb. Okay, so you got it?
We haven't
Got
turned
it.
ours up yet.
What's that?
We haven't turned it up yet.
Oh, you didn't turn it up? Okay,
Oh, that's why you're
turn
still
it up. Okay, I thought you had. Not much, just a little bit. What happens to the bulb if you turn it up? It gets brighter. It'll stop right there. Stop right there and turn it off. Okay? So, when you double the voltage, you would make the bulb brighter. Right? Is that what your observation was?
Brightness.
Brighter. Okay. Then set up number 4. Now, number 4
Two
is
bulbs.
set up just like 2. Turn it off, yeah. Number 4 is set up just like number 2, except this time I do want you to double the voltage from what it was in number 1. This time I want you to double the voltage, set it up just like number 2 was. Double the voltage.
How much?
Huh?
How much?
Double the voltage. Did you record what the voltage was originally?
Yeah.
What was it?
6.9.
Second?
6.9.
That was it
Well,
originally?
the original was 6.5.
Okay, double the voltage. What was your original? 5? Okay, that's good enough.
But it got brighter.
Okay, brighter than standard? You're up at 12.
It stays.
What's double 4.5? 9. Okay? Did you double your voltage? What did you tell about the brightness? It looks like standard. What happens? What's your other thing observation? Okay, what happens if you remove the bulb? Have you done it? All right, good deal. Turn it off then. Turn it off. Don't leave the bulb flow.
Okay, they go off.
Okay? What did you get?
Standard.
Standard brightness?
Yes.
And what happened if you remove the bulb?
It went off.
It went off. Good deal. Now, we're going to set up number 5. This is different. This is what we call a parallel circuit. Do you know how this works? You do. Okay, set it up and let me check it before you do it. Okay? Okay? That's at least part of it. Okay? You don't need those little wires. You'll probably need 2.
Does it matter what color?
I doubt it does, unless you want to color code them. Okay, now, here's one thing I would do. There's an outer one here, and you get yourself in that room. So here, and this is the current going to be, this is the one that is going to split. So Alright, now, notice that your high end on this one, where's your diagram? The positive end here, that's the red here, is connected to both the upper end of this one and that one. So, what I'm going to do is use this other one here. So we have a little more room. There we go. Okay. So, if you wanted to wire, I'd do the red one. So, do it here. And then the low end here. Low end there. There you have a parallel circuit. Right? Okay. This is going nowhere, and this has nothing going to it.
You have to use the wires.
Start with this one. Notice parallel with high end is connected to high end in your diagram. The positive connection causes the positive yeah. The high end here. Okay, you got it done?
Okay.
No, I haven't seen it.
Okay. No, this is serious. You don't have a parallel. Because the parallel, your high end is connected to high end. So put that somewhere, anywhere. Not there. Okay. Not there. Not there. That's serious. Okay? Go somewhere other than that, so it's not serious.
You just gotta do something opposite different. He's gonna run 2 jumper wires in and hog the ground.
Okay. Alright. So you need something in your diagram. The high end here from the battery is going
I mean, I was biting on it.
They do for at least a quarter.
there. And your low end here.
name He's over there by Lake
Okay. All right, we're doing number 5, right? Listen up. We're doing number 5?
Yes.
Okay, you got your parallel circuit set. I think I've checked them all. Now, what voltage do you have? Say again?
They all break.
No, wait. What was your original?
You ain't got one now.
Okay, you're about the same as you had in number 1, right?
9.0.
5.2. Oh, not yet. 5.2. Yeah.
We still landed on the last one.
Okay.
It's 9.2.
No. So what you had in number 1. See, it's the same voltage. Turn it down. Okay. What was your original voltage? That's why I said listen up.
5.2 volts.
5.2 volts. Okay. You got your standard voltage. How is your brightness?
Standard.
Okay, standard. What happens if you remove 1 volt?
I'm always going to stay on.
Look at that. Okay. What happens if you remove 1?
It stay the same. It stay on.
It stays on. So there's your 2 observations. What was your brightness? Turn it off once you made your observations. What was your brightness?
Brightness and turn on.
Standard brightness, and the second bulb stays on. Right? Okay. Let's move to number 6.
Yep.
Now, number 6, we're going to do turn it off when you're through.
I'm sorry.
Okay. Number 6, we're going to do it just like we did number 3. We're going to just increase the voltage. Same setup. Just increase the voltage. Don't necessarily double. Just increase enough till you can see what the bulbs are doing. Understood? So turn them on. It should be at standard. Then increase just until you see what the bulbs are going to do.
Look at the bulb.
Increase. Okay, what happens?
You got brighter.
It gets brighter. Stop there. Don't go to double. Okay, remove a bulb.
Remove it.
And what happens?
It stays on.
Okay, so turn it off once you make your 2 observations.
Brightness it stays on.
Okay,
It's it.
now, everybody got it?
Yes.
Okay, now, number 7. We're going to think through and not actually do it. And there's a reason for it. Take a look at number 7. What do you notice there? Yeah, 1 bulb is in parallel with a straight wire. No bulb up there. Now, here's why we're not going to do it. What do you think is going to happen here?
You gonna blow the fuse?
Okay, you could easily do that. Why?
It's a short circuit.
Yes, it's called a short circuit. We haven't talked about that in class yet. What do we mean by short circuit?
And increased resistance.
Second? Okay. Okay. Basically, I heard resistance mentioned too. We haven't talked about it in class, but it's certainly there. What you're doing is providing one pathway with hardly any resistance at all. The second pathway is going through your light bulb, which has resistance. Now, I say this, I don't know, I hope not to be offensive to anybody, but I say that current is a lot like a student. It always follows the path of least resistance. Oh, students like that today? Or back when I was in school, but I didn't know it was still that way. Okay, so what is the current going to go? Through that wire where there is no resistor, and lots of current can go through there because there's no resistance. Therefore, it would get very hot, and the bulb wouldn't come on because what current wants to go through resistance when it can go through the straight wire?
So it's
Okay.
it's a high current and less resistance for a short
Absolutely.
circuit.
When you have the straight wire through there.
Right.
So therefore, what would happen to the bulb?
It buzzes.
No.
It would stay off.
It stays off because the current goes through the straight wire. It doesn't go through the bulb. bulb is offering too much resistance. Now, in reality, maybe a teeny bit of current might try to make it through there, but you wouldn't be able to see the light bulb come on. So this one, your observation is what?
Stays off.
Stays off. The bulb stays off. Now, notice what else it says on number 7 on page 183. Show with arrows how the current takes the path of least resistance. So either you draw the diagram like you had number 7 on page 180 there in that block 2. You already said that the bulb wouldn't come on. But then you can either draw the circuit and show which way the current flows, or you can do it on number 7 if you want to. Draw a little arrow showing where the current flows and no arrows where it doesn't flow. Does that make sense?
So, you can draw one.
You have more room to draw it on number 7. No, you're number 7.
Number 7, okay.
You got to understand what it's asking for? Where does the current flow? Say again? Through the straight wire and not through the bulb. Got it? Okay. Now, basically, if you look at number 8, it's just an expansion of number 6, except they put a switch on each one, and since we're not doing switches, it's identical to 6, right? Okay, so you can either do it again, what you just did for 6, or just write down what you had for 6.
Which is circuit 8?
Number 8 is just like 6. Only thing is they got an extra switch in there, but we're not doing switches, so it's exactly like 6. So fill in the data for it. Okay. Does that make sense?
Yes.
If you have questions, please ask.
I have a question.
Okay.
Do you want me to just draw the circle, or you want me to write it out for you?
Okay.
For the current.
Show with arrows how the current takes the path of least resistance. So you could have either drawn it there, or, like I said, you could go back here and draw it here, where the current goes.
Okay.
I'll tell you one thing. It leaves the battery and goes up here.
To the wire.
Yeah, okay. But and so draw the arrows there and no arrow through the bulb.
Okay.
Yeah.
Sounds good.
Okay. Is this making sense or not? Okay, everybody got it? All right. Now, the important thing is that you have your table 20.1 on page 183 completely filled out with the data that I asked you to put there, right? You got it? Everybody got it? Everybody got the data in the table? Everything I asked for, right? You got, and everyone, you should have dimmer, brighter, standard, or doesn't come on. And you should also have what happens to the second bulb when you remove the first bulb when you remove the second, or vice versa, when you had 2 bulbs. Okay. Once you got all those data in that table on your observations, then go back to page 181. Using the brightness of the bulb in the simple circuit 1 as the standard for normal, write which circuits had bulbs with normal brightness. You should have all that in your table. Which ones had normal brightness? Based on your table. Everybody got it? And by the way, your circuits are numbered 1, 2, 3, 4, 5, 6, 7, 8. Okay? Now, everybody got number 1 done? Okay.
What he said? I got a question.
Yes.
Can you repeat what you just said? Because I was drawing the
Okay.
thing.
All right. On number 1, results on page 181. Okay. I asked before, did you have all the data filled in on your table on 183? You got in every observation, all 8 circuits, you have whether it was standard, brighter, dimmer, or not come on at all.
Come on. Yeah.
You got one of those in every block.
Yes.
Okay, and the blocks with 2 bulbs, and they all list whether they have 2 bulbs. That's to be number 2, 4, 5, 6, and 8. Okay? You have whether the bulb went off or stayed on, right?
Right.
Okay. So with those observations that you had there, number 1 said which of the circuits, and it's numbered 1, 2, 3, 4, 5, 6, 7, or 8, had standard brightness. Okay.
Next.
Everybody got number 1 done? Number 2, which circuits had bulbs that were dimmer than normal? Look at your observations. You wrote them in, you said. Okay, you got them. Now, that has a second part. Explain. Why were the bulbs in those circuits dimmer than the standard? Second? Okay. It's not power, it's voltage or energy. Those would be good answers. Power is not quite the right word. Okay? It's split between 2. Why? Because the current had to go through both. You doubled the resistance effectively, so therefore, well, we didn't talk about resistance. So anyway, that's it. Okay? Number 3. Which circuits had bulbs that were brighter than normal? Look at your observations on your data table on page 183. Which ones were brighter than normal? Everybody got it? That one also has an explain. Why? Everybody got that done? Huh?
The bulb stayed on when you
Okay. Have you finished number 3?
Yeah.
Okay, did you explain why it was brighter than normal? Number 3 says, which circuit says bulbs brighter than normal? Put the numbers of the circuits there. 1, 2, 3, 4, 5, 6, 7, or 8. Whichever ones. But then it says explain. Please explain. Anyone have trouble explaining?
Yes.
Okay, what's...
I don't know why.
You don't know why.
I think
What you notice about those circuits that were brighter than normal?
it's high voltage.
Okay, yeah. You had more energy going through the circuit, right? Okay. Sounds like a reasonable answer. Okay, number 4. In which circuits did removing one bulb cause the others to go out?
Less current.
It says in which circuits? That's the number 1, 2, 3, 4, 5, 6, 7, or 8. You through with it? You sure?
Yes, sir.
Okay. Good deal.
Which circuit and what?
In which circuits? It indicates numbers. List which circuits that would be appropriate. Did one bulb removing one bulb cause the other to go out? You said you put it in your table. Indicate from the table. You got to go. Take that test real quick? Right. Well, you don't have to do it real quick. Okay. It's test 3, right?
Yes, sir.
So if you want to go back to the classroom, you can. That's a little easier sitting than in here.
I disagree.
Okay, you like it better here, okay? I know you don't want the key, you just want the blank. Okay. Okay? You can use a formula equation sheet, absolutely. Okay? We were on question 4. In which circuits did removing one bulb cause the other to go out? You listed the circuits, right?
Yep.
Then did you explain why? Any ideas? Why did removing one bulb cause the other bulb to go out?
Because you cut the current.
Second?
You cut the current from the other bulb.
Okay. They were series circuits. The same current went through everything. You remove one, you broke the circuit. Okay? So there's no pathway. Say again?
Is this what Alabama Power do?
I can't hear you.
Is this what Alabama Power do?
Is that what they do? Yeah, in some senses. They provide energy. Yeah. Okay. Number 5, in which circuits did removing one bulb not affect the other? Good deal. Thank you. Go back and check your data sheet, your observations. Pardon? I can't hear you. Okay. You through? With all of them? Okay. Finish off? Okay, good deal. You got it? Okay. Okay, number 5, did everybody write the circuits which removing one bulb did not affect the other?
Yes.
Okay. Did you explain why?
Because it had a pathway.
Okay, there was still a pathway for the second bulb. Good answer. That's called parallel circuits.
What you just said?
Say again?
What you just said?
She said there was a pathway for the current to go through the other bulb. When it was in series, you remove it, there's no pathway. You broke the circuit. But when the parallel circuits, there was still a pathway for it to get to the other bulb. Okay? Number 6. Describe the general requirements for any circuit to function. Anyone got any ideas on that? Say again?
The wires.
Okay, you gotta have a wire or a pathway, absolutely.
The wire pathway.
All right, that's required. Anything else?
A ground.
Well, we're in direct current.
Oh, my bad. I'm
Yeah.
talking about something else.
A battery and a bulb.
A battery and a load, or a bulb or a load. That's perfect.
What about a voltage source?
The what?
A voltage source.
I can't read.
A voltage source.
Yeah, that's right. She said a battery for a voltage source, the same thing.
Oh.
You could say power supply, that would be fine too. It's not as, and then be sure you answer number 7. One way or another, but you have to have an answer on 7. That's up to you. Good deal. Make sense? Was it worthwhile?
Yes.
Good deal. If you have questions, please ask. And remember, next time we'll have 2 hours of class, 2 hours of lab, and then 30 minutes of test on chapter 4. Okay, does anyone need me to answer anything again? I'll leave this on if I need to, or I can go on and start uploading. Any questions? Y'all got it? Okay. So I'm going to shut it down. Is that what I heard?